So from 8.1, I think up to 8.3 or 8.4, there's a new short that's been released on AMALearning. It's on the topic of energy, and that covers it really, really well. So after you've finished here, I would advise having a quick look at it, and you'll see how it recaps it really, really well. So scenarios of energy transfers. An object is projected upwards. So what are the energy changes here? When we throw it upwards, for the ball to move upwards, that is equivalent to that's kinetic energy. So you need to provide kinetic energy for the ball to start moving. The higher it goes, the more potential energy it will have. So it goes from kinetic to potential energy. Next one. An object is projected up a slope. Again, kinetic energy to gravitation, potential energy. So it's like this roller coaster as it goes up and up and up and up and up. So if anyone's been to Blackpool and seen the Pepsi Max, as it's going upwards, to move up, it's kinetic energy. When it gets to the top, just before it drops down, it's got a maximum amount of potential energy, which then converts back into kinetic energy as it falls downwards. So another one, a moving object hitting an obstacle. So here, kinetic energy because the car was moving, and once it's collided with the wall, you'll hear the sound of it. That's one thing. And also, one thing to always keep in mind is friction. When particles collide with each other, so even your hands just colliding with each other, what does that mean? That means that whenever there's friction, it means heat energy is being dissipated, heat energy is being lost. So here, as soon as you have a collision there, heat energy will be lost. Next scenario, an object accelerated by a constant force. This does depend on context, but for example, this example is a boat. The boat has petrol or diesel or kerosene inside it, and it uses that fuel and it converts to kinetic energy, which allows it to move. Again, this one is on context, an object accelerated by constant force. For example, well, this is not concentrated, this is not an object accelerated by constant force. This is the person falling out of a plane with a parachute. As the person increases in speed and falls downwards, the potential energy decreases. So gravitational potential energy converts into kinetic. When the person's at the top in the plane just for the jump, they've got maximum gravitational potential energy. And that's because gravitational potential energy equals mass times gravity times height. So height is at a maximum. As height becomes less and less, gravitational potential energy also decreases. Because mass doesn't change, the gravity of Earth isn't going to change either. Vehicles slowing down. So this is kinetic to thermal. Because as you get more and more friction between the wheels and the ground, which is a force, more and more friction, more and more force between the tire and the ground, it's exactly what I said before. Heat energy is dissipated. So the energy levels decrease. So the car slows down. Bringing water to a boil in an electric kettle. So here the electric current is being converted into thermal energy. Okay, so how can we represent energy transfers as diagrams? We can use Sankey diagrams. Now, when you have a Sankey diagram, this whole section here, let's call it number one, this represents all of the energy in a system. So it's all of the energy. And then what it does, it splits it into this section here, which is useful energy, and this small section here, which is wasted energy. Now you see the width here. If you add the width from there plus the width from here, it equals the same as number one. So number one equals 2 plus 3. So when these are drawn, they're usually drawn to scale so that we can actually calculate how much energy is being used. And this automatically falls into the efficiency calculation as well, which we have covered previously, but very quickly, efficiency equals useful divided by total. So this number here divided by this number here. And how is energy usually wasted? It can be wasted through sound. Not always. For example, in a TV, sound is not wasted energy. Most of the time it's thermal, but again, in a radiator, we wouldn't class it as thermal. And sometimes energy can be wasted as light. So the definition of conservation of energy. The law of conservation of energy states that can energy cannot be created or destroyed. It is only transferred from one form to another. The total amount of energy in a closed system remains constant. So what we're saying here is when, for example, we eat food, okay, so that's supposed to be a burger, but never mind. Okay, person eats the burger. Now, as soon as they've eaten it, taken a big munch out of it, then we use the energy that's in the burger, that's chemical energy, and we use the energy for movement. So we move it, it's used for kinetic energy. We use it to keep our body warm, so that's thermal energy. And if we add this energy up plus this energy, kinetic and thermal, it'll be equal to the same amount as the chemical. So the energy is not wasted, it's just transferred into new forms. Now in an exam, you can write heat energy, and you can write thermal energy, it's the same thing, as long as the word energy is there. This means that whenever there are energy transfers in a closed system, that there is no net change to the total energy. So energy in equals energy out. Now, energy can be transferred in one of four ways. Mechanical work. So this is when a force moves an object. So there's a box, and a person pushes it with their arms. So that's not, it doesn't look like it's pushing, it looks more like he's, actually, I'm not sure what that looks like. Okay, then we got electrical work. This is when a charge moves due to potential difference. In other words, electricity flowing through a wire. Heating. This occurs due to temperature differences. And radiation. Energy transferred as a wave. So energy is transferred by one of these four different pathways. Okay, 8.5, work done. Work done equals force times the distance. So, for example, I'll draw it a bit better this time. Here's a box. Let me drop that out 1 second. Here's the box. It's on the ground. And we want to move from here to here. So a man comes along and starts pushing it. That's what I was trying to draw before. Oh, I've added extra arms. So the man starts to push it. Now, the force that this man applies is multiplied by the distance that box is going to move across. Force times distance. And it gives us work done, and work done is measured in joules, energy. So 1 joule of work is done when a force of 1 Newton causes displacement, or the displacement as in the movement of 1 meter. So that's the distance, force times distance. So 1 joule is the same as a Newton meter. Work done against a frictional force acting on an object will cause a rise in temperature of the object. So you go back to this example here. This person is pushing this box, but the person pushing the box has to overcome the friction between the box and the ground. Now, what that means is the energy, the work done, some of the energy is lost as heat energy. So generally speaking, when we say Generally speaking, when we say, so what we're saying here is that this person is pushing the box from here to here, so that's a distance, and they've got to exert a force, put a force into it to move it across. And that gives us work done. Work done is the force times the distance. When we work out the work done, we work it as joules, which is the same as an energy. So now if we say potential energy of something was 900 joules, the next question might say, what was the work done? The answer is still 900 joules. Because work done, because the difference is this. Let me just get rid of all this because I want you to really quickly understand this. I'll take a little bit of time to explain this. In the way that work done, how our work done and potential energy interchangeable. So if a person gets a box, actually let's look at it as weights. There's a weight on the ground. Someone picks it up and lifts it high, lifts it above the head. Okay, from a work done perspective, they've applied a force over a distance. So that's force times distance. And that gives us the work done. Now, let's look at this from a mass times gravity times height. That weight that's on the ground, it has a mass. Gravity is always 9.8 because we're on Earth. It's lifted through a height till it's above the person's head. So when you do mass times gravity times height, we get potential energy. So in this scenario, potential energy and work done are the same. So if I told you the potential energy of the man lifting this weight is 900 joules, if my next question is, what is the work this man has just done, or this woman or this person has just done, what would the answer be? It's still 900 joules. They're interchangeable in that respect. The difference here is this, is what it says there. Work done, this bit I'm just rubbing out. Work done against a frictional force acting on an object will cause a rise in temperature of the object. So any friction that occurs as this person lifts this barbell above the head, the weight above the head, will cause some of the energy to be lost. So although the answer is correct to say 900 joules, it will be 900 joules in a closed system. If it was an open system, the answer won't be 900 because some of the energy will have been lost. So question one might be work out the potential energy because they say the man lifts it for 2 meters above his head. It has a mass of 500 kilograms. Actually, that's a lot. 50 kilograms. So the person works out 9.8 times 2 times 50, we got an answer. Then whatever the answer potential answer, the question 2 might be, what's the work done? You say 900 joules. Question 3 might be, why is the work done always a little bit less than the potential energy? And that's because any friction that's occurred has meant that some of the energy dissipates as thermal energy. Some of it's lost as thermal energy. Okay, now this is the formula. Work done equals force times distance. Don't forget, meters are in it's distance in meters. Now, if you're struggling to convert meters to kilometers, to millimeters, to micrometers, nanometers, etc., then if you go to the AMALearning website, the YouTube channel, there's a video that's entitled 1.3, 1.4. Can't remember the name of it, but if you find 1.3 and 1.4, it's all in one. That is a good 2-3 minute video just to show how to do conversions. Okay, now I'm going to go through one practice question. I'll leave these for you to go through in your own time. Calculate the work done when the force equals 72 and the distance is 150. So the first thing we've got to do is convert 150 into meters. How do we do that? We divide by 100. So it's 1.5 meters. So let's substitute our numbers in, our values in. F equals 72. Distance equals 1.5. Do the maths. And what do we get? 108. Someone can check that if you want. And it's 108 joules. So the remainder you can have a go at yourselves. This one's calculate force, this one's calculate distance, so you'll have to rearrange the formula to get the correct answer. Okay, definition of gravitational potential energy. So this is now just a formula, which I've already explained to you. Gravitational potential energy, M is mass, G is gravity, H is height. Now on Earth, gravity is always 9.8. Now whenever this question comes up, it's usually a maths question. And we know what weight is, it's mass times gravity. And when we're calculating, got to make sure that mass is in kilograms. That's why here 350 has been divided by 1,000. And this question here, for example, you've got mass, you've got the height, and you've got gravity. So it's just M times G times H. Multiply the three numbers together and you've got 9.604. To two significant figures, 9.6. Okay, there's another example. Except here we'd calculated the mass. So you're going to rearrange this formula. So potential energy equals, mass equals potential energy divided by the gravity times the height. So lots of practice there for you to do. And then it takes us to kinetic energy. Now, what you've got to keep in mind when you're answering potential energy and kinetic energy questions is this. When something's at maximum height, it has maximum potential energy. As it drops, just before it lands and hits the ground, it's got maximum kinetic energy. So in a question, in part A, you might be asked to work out the potential energy. In part B, now if you're working out potential energy, that means it's giving you the mass, it's giving you gravity, it's giving you height. You worked out potential energy. Now in part B, it might say, work out the velocity of the ball. So it might be you threw the ball upwards, write down what his maximum potential energy was. And the ball was 2 kilograms in mass. It's going to be 2 times 9.8, and we threw it 5 meters up in the air times 5. So that gives us 98 joules. Yeah, hope everyone's following what I'm saying here. Now the second part of the question, it might say, you've just worked out gravitational potential energy. Now work out the velocity of the ball. Now, you might be thinking, what do I do here? Because what's velocity got to do with it? Velocity equals distance divided by time. Um, Kinetic energy equals, however, half times the mass times the velocity squared. Now, in this, at the moment, we've got mass, which is 2 kilograms. We've actually got kinetic energy because don't forget, all the potential energy, what does it convert into? Kinetic. So the potential energy that you've just worked out to be 98 joules, the kinetic energy also equals it. So 98 equals half times 2 times the velocity squared. And then you can rearrange it to find out velocity. So this is the formula for kinetic energy. So kinetic energy equals half times the mass times the velocity squared. Again, lots of practice here. You've got to make sure mass is in kilograms. So divide grams by 1,000. Substitute numbers in and make sure you do write your answer to two or three significant figures. So lots of practice here. Okay, dissipation of energy. Now, this is just one of those topics that's really common. Comes up quite a lot. It's important that we understand it. So when it comes up, we easily get our marks. Easily get our marks. So what is the law of the of conservation of energy? So this, we're not going to talk about conservation, we're just going to talk about dissipation. So if I throw a ball, it starts here, it bounces. When it bounces, it goes to this height. It bounces a second time, it goes to this height. It bounces a third time, it goes to this height, and at the end, it just rolls. Why is that happening? That's because when the ball hits the ground, some of its energy dissipates. It's lost to the surroundings. It is lost to the ground. In this case, the ground absorbs some of the energy. As it falls through the sky, through the air, it hits air particles. Every time it hits an air particle, it loses some of its energy to its surroundings. So this is what we mean by dissipated energy. So when all system changes, energy is dissipated. That means it's lost. The energy is stored in less useful ways. So it converts into a less useful form. For example, in this TV, energy is wasted as thermal energy. So if has anyone ever put their hand at the back of a TV and noticed it's really warm, really hot? That's because energy is being wasted as heat energy. Same thing happens with bulbs. Sometimes you might, you know, for example, you might be in school or might be somewhere where the radiator is making a noise. I know the radiator in my classroom, although it hasn't in the summer, actually I've not heard it for a while because I've not been putting the heating on in the classroom, but during the winter when I had the heating on, it will start making a rattling sound. Now, if it's making that rattling sound, it means energy is being wasted, energy is dissipated, it's lost in a less useful manner. Okay, mechanical processes. So before we continue, this is important that you understand this because I've seen this in so many questions. Hopefully, we'll see them during the pre-exam workshops as well. We're going to see where at the end of some maths questions, the final part of it is why did the energy decrease? Why is the energy not exactly the same? And that's because possibly due to friction, due to the energy being absorbed by the ground, whatever it is, energy is lost to the surroundings. Energy is lost to thermal energy. Energy is dissipated. Any of these things are answers. And it will come up again and again and again and again. Okay, 8.11, mechanical processes. How is energy wasted in mechanical processes? So mechanical processes become wasteful when they cause a rise in temperature. So energy is dissipated into the surroundings as heat. So similar to what we were saying before. So if you've got a mechanical process like this spins. This spins, and as it spins, what's it doing? This part of the plastic here. Oh, let me do that more. Let me try that again. This part of the plastic is rubbing against this part of the plastic. You've also got a metal here that will be rubbing against things. And every time they're rubbing against each other, you have friction, and so energy is lost as heat. Now, let's say 100 joules of energy enter here. Okay, 100 joules of energy are, from the 100 joules, 80 joules are converted into kinetic energy in causing that to spin. So kinetic energy is 80 joules of energy. That means how much energy has been lost as heat, as thermal energy? 20 joules. So what came in? 100 joules. What's come out? 100 joules. So energy has still been conserved. The problem, what we're trying to show here is that this is less useful. This is wasted. It's dissipated. So if we do a Sankey diagram for it, what it would show is that 80 joules of energy go that way, 100 joules came in, and 20 joules are being wasted. So overall, though, energy is still conserved. Okay, 8.12 and 13 are linked to power. So what is power? So we can work out power as power equals work done divided by time. Because essentially power is the amount of energy used per second. So a watt is the same as joules per second. So it can be work done divided by time. Power can also be energy divided by time, kinetic energy divided by time, potential energy divided by time, just any energy divided by time. But don't forget, time is measured in seconds and power is measured in watts. It's very common in power questions to get megawatt, which is times 10 to the power of 6, or in other words, millions of, or you can get kilowatts, which is 1,000. So the rate at which energy is transferred or the rate at which work is done, that's what power is. So it's joules per second. You can use either of these formulas. So here's a quick practice question. We've got 1.5 times 10 to the power of 9. So let's rewrite that because that 9 is not good. 10 to the power of 9 watts. And we've got 5 hours. Now let's go back. What do you measure time in? Measure in seconds. So hours is not going to work for us. So that means we need to do 5 hours. There's 60 minutes per hour and 60 seconds per, sorry, 5 hours, 60 minutes per hour and 60 seconds per minute. So we're doing 3,600 times by 5, which is 18,000 seconds. Now power equals energy divided by time. In this case, we're trying to work out energy. So energy equals power times time, which in this case is 1.5 times 10 to the power of 9 divided by 18,000. Then you do the maths. Your answers is going to be energy, so it needs to be joules for the units. So we get, sorry, I've divided this. It should have been times. Yeah, because I wrote times there and I didn't end up timesing it. So times 18,000, which equals 2.7 times 10 to the power of 13 joules of energy. Okay, so this is what is the relationship between a watt and a joule? Watts are joules per second. And efficiency, we've already covered this also. Efficiency is the useful output divided by the total input. So if you look at your Sankey, let's look at another Sankey diagram. I can't seem to draw these correctly. So let's say our total energy in was 90 joules, useful was 60, and wasted was 30. What we would do here is 60, that's useful, divided by 90, that's the total. So that's the total there. That's useful. This is just wasted. So we can ignore the wasted energy. But we know energy is wasted through light, sound, and more often than not, thermal. Okay, so well done. If anyone has any questions, please ask now. So, Physics Edexcel Paper 2, Forces and their Effects. So 9.1 is linked to the interaction of objects. Now, in this topic, 9.1, 9.2, 9.3, 9.4, 9.5 is all combined, and then 9.6, 7, 8, and 9 are triple award. 9.10 is also combined. So what I'll do after 9.5 is briefly explain 9.10, and that way combined students can leave the session, and then I'll finish off this topic with triple award. So we're going to do 9.1 to 9.5. I'll then explain 9.10, and that way combined is finished, and then I'll finish triple off after that. So what we're covering now is Physics, Edexcel Paper 2, Topic 9, Forces and their Effects. So forces. A force is a push or a pull that acts on an object due to the interaction with another object. So in other words, if I have a door, if I pull that door or push that door, that's my interaction with that door. I've pushed it or I've pulled it. That's a force. But you have different types of forces. You've got contact forces, where you have to physically touch. So for example, me pulling open a door or pushing the door shut, or vice versa. And non-contact forces, which are the ones where there's no touching happening. For example, what happens between magnets. So we've got different examples of contact and non-contact. Friction is a contact force. Air resistance and water resistance, which are both examples of friction, are contact forces. Tension, so that when you stretch or you compress a spring, or you pull a wire, pull a string, sorry, or rope, piece of rope, that's tension. And normal contact force, like pushing and pulling. And our three main non-contact forces are gravitational, electromagnetic, and magnetic forces. Static electricity and static force has a similar behavior to electromagnetic and magnetic forces. So they're non-contact forces as well. So forces arise from an interaction between two objects. When two objects interact, both experience a force. So friction is the interaction between two surfaces that slide relative to each other. Each surface experiences a force in their direction that prevents relative movement. So what we're saying, this is what I was saying to you guys before. When particles touch, we get friction. And that friction, what does it do? It dissipates heat energy, it loses heat energy. But what we're explaining here now is that the box we're trying to push this way. But because the particles touch each other, they have opposite but equal forces on each other. So it goes back to Newton's third law, and that slows down the movement of the box or stops it from moving. So here there's an interaction between an object and the surface it is resting on, so the cat and the table. The object pushes down on the surface and the surface pushes up on the object with an equal force. Opposite in size but equal in opposite in size but opposite equal in size, opposite in direction. So the cat has a downward force, the table has an upward force. That's so the force is the same but the opposite directions. That's a normal contact force. Now, all forces, all measurements are either scalar or vector. So we have covered this before. Scalar is only when it only has a size, a magnitude. So this was covered in paper 1 as well, but it's very important with paper 2 also. A vector quantity is something that has magnitude or size and also direction. So for example, if I say to you, I've gone for a walk, I walked for 100 meters. Does anyone know where I've gone? No, because I've only give you a size. I've only give you magnitude. If I now say I walked 100 meters due east, now you know magnitude and also direction. Now a vector quantity may be represented by an arrow, and this is why this is important. A vector quantity is represented with an arrow, and the bigger the arrow, the bigger the vector quantity, bigger the force, bigger whatever it is. So quickly, let's look at some scale and vector quantities. Again, it's something that we covered in topic 1, but it is repeated here because it's so important to paper 2. So we covered it in paper 1, it's important in paper 2 as well. Mass is scalar, density, temperature, energy, distance, speed. They're all scalar because they're just quantities. They tell you how big it is, but it doesn't give you any feeling of or understanding of direction. Then we've got vector quantities such as momentum. Now, one thing to notice, remember here, is momentum equals mass times velocity, and velocity is a vector quantity. So if you can't remember in the middle of the exam if something's a vector or a scalar, have a look at the formula booklet. So if you forget what momentum is, check what momentum equals. Momentum is mass times velocity. Velocity is a vector. So that means momentum is a vector. Acceleration equals change in speed, in other words, v minus u, divided by time. So again, we've got v, got speed, change in velocity. So acceleration has to be vector. Force, there's a few different equations, but force equals change in momentum divided by time. Momentum is vector, so is force. Force also equals mass times acceleration. Acceleration is a vector, so is force. Displacement is like distance, but it has a direction. And weight, now mass is how many particles something has. So sometimes we weigh ourselves in kilograms. We're not actually weighing ourselves, that's our mass. Now, weight is when gravity pulls on those particles. When gravity pulls on those particles, we call it weight. And which direction is gravity pulling? Downwards, so it has a direction. So weight automatically is also a vector quantity. So now if you've got a vector diagram, here you've got the forward force from the engine, 1000 newtons. You've got air resistance at the back here of 750 newtons. Now we could replace that all with one arrow called resultant force. So the forward force minus the backward force equals 250 newtons in the forward direction. So that one arrow replaces these two. We don't need them. We can just put that one arrow there and done. Notice how the 1000 arrow is bigger than the 750 arrow. Now, if forces are acting in the same direction, you add them together. If forces are acting in the opposite direction, we subtract one away from the other. So let's have a look at this. A parachutist has a weight of 70 newtons. And air resistance as they fall is 18 newtons. So let's look at number 1. Let's look at number 3. So there's the parachutist. I can't draw a parachutist, so I'm just going to do it that way. As the person's falling, they have a downward force of 70 newtons. And they have an air resistance, an upward force of 18 newtons. So all we're going to do is 70 take away 18, which equals 52. And which is the direction where we've got a bigger number? Downwards. Okay, let's look at this one now. Let's draw a car. The car's forward force is 100 newtons, but air resistance is 22 newtons. And from the tires, we have friction on the road of 32 newtons. So what we're going to do, because they're in opposite directions, we're going to take them away. 22 plus 32 is 54. So we're going to do 100. So you can add these two numbers up. You can either do it as 100 take away 22, take away 32, or you can add them up and say 100 take away 54. So that means we've got an answer of 46 newtons in this direction. So what forces act on objects? Within your exams, you need to be prepared to identify and label forces acting on objects. So here we've got weight going downwards, we've got air resistance going upwards, resistance. So weight acts downwards on an isolated object. Resistance acts in the opposite direction of motion. So whichever direction something's moving, so a car's moving this way, as the car moves that way, it's going to bump into air particles. And that's what we call air resistance. So it means it exerts a force in the opposite direction. And how do we calculate? How do we calculate the resultant force if forces are not acting on a straight line? So let's look at this question. You would draw a vector diagram to find the magnitude and direction of the force. You can use trigonometry here. So I personally always use trigonometry. I've always taught high ability students who are very good at maths to use trigonometry. The issue is sometimes they give you graph paper sections to draw this out in during exams. So if they expect a drawing, then you're gonna have to do it like what's shown here, unfortunately. Because otherwise, if you look at that, that's 60 newtons that way, 30 newtons that way. What you've actually got there is a right angle triangle. So not trigonometry, sorry, you can use Pythagoras. Because you're looking for the hypotenuse. So you can just do c squared equals a squared plus b squared. So I've done it lowercase here, but not a capital there. So you can do this question in that way as well. However, it's in science, unfortunately, it's better to draw the graph out. So now a skydiver jumps from an aeroplane. There's a resultant vertical force of 300 newtons on the skydiver and a horizontal force from the wind of 60 newtons. So let's just zoom into this and do our own. Let's say each line equals 60. So we only need to go across by 1. That's our 60 done. Now, to get to 300 downwards, we need five of those lines. So 1, 2, 3, 4, 5. And that's our 300 newtons. Now what you do is from this corner here to this corner here, as in you draw a line, like the one that's drawn here. Now, say one of these sides is 1 centimeter. What we do is we measure that line that's in between. So this one I'm just about to draw there with a ruler, and for and let's say it works out to be 10 centimeters. We do 10 times 60. If it works out to be 5 centimeters, we do 5 times 60. That's all you've got to do. Now, in this case, once this has been measured with a ruler, it was just over 5 centimeters. And hence, there's an answer of between 304 and 308. Okay, how do we calculate the resultant? So this is 9.4, 9.5. How do we calculate the resultant force if forces are not acting on a straight line? So apologies, 9.3, 9.4, 9.5 are all triple, sorry, not triple, higher topics. So 9.3, 4, 5 are all higher. Now, how can we calculate the resultant force if force is not acting on a straight line? So a free body diagram models the forces acting on an object. The object can be shown as a box or a dot. So here's the box, and these are the forces acting on it. It helps to have arrows drawn to scale where possible. The easiest way, what they're trying to say here is that sometimes you've got some forces not acting in a straight line. You might have a force acting that way, a force acting this way. Now, the best thing to do when that kind of happens is this. You use vector diagrams or Pythagoras theorem. Now, 9.10, the specification point for 9.10 is explain ways of reducing unwanted energy transfer through lubrication. All it means is if you lubricate two surfaces, what happens? They slip past each other with less friction. So in a machine, if you lubricate with oil, you've got less friction, so less energy is lost as heat. And that's essentially what 9.10 is. Okay, so so 9.6p and 9.7p. 9.6 and 9.7p. So this is physics only. Moment of a force. So what are moments? There is a turning effect of a force. And we calculate that by doing force times distance. Now let's look at what turning effect actually means because it's not fully understood. What it means is if you have a pivot and something's attached to that pivot, so let's say a door. I'm looking at the door from above. When we apply a force, what's going to happen? Let's say we apply a force from here. What's going to happen? It's going to cause the door to move in a circular motion. That's what I mean by turning effect. Now, the next thing you need to remember is this. Here's the pivot. Here's the distance from the pivot to the force. Okay, that's distance. This is the force that's just been applied. The bigger the distance, the bigger the overall moment. So if I pushed from here, try to close the door from here, now my distance from the pivot is smaller. So that means my moment is also smaller. So for example, if we're trying to open up a bolt and it's really jammed in, if we use a small spanner, that looks more like a little person. If anyone watches Pokemon, that looks more like Meltan. But that is not what I was trying to explain. So if you've got a spanner, for example, and it's only got a short handle, where your hand is, that's where the pivot is. So your distance is only this much. If you increase the length of the handle, your pivot's going to be here. You've got all that distance. So you've multiplied the force that you're applying by so much more. So it's important to, if you want to like use this moments to your advantage, you increase the distance. So this is just an example question, and don't forget meters are measured in. So distance is measured in meters. So calculate the moment when force is 750 newtons, but distance is 135. So we're going to divide that by 100. There's our formula. Substitute the numbers in. Force equals 750, distance equals 1.35. Multiply together. Round to the nearest um, decimal point. Here you can do one decimal place. You can do two, three significant figures. You would get the mark here for just writing 1010. In where you've got these larger numbers, I would go for at least one decimal place, unless the question says differently. Some practice questions, examples here for you. I'm not going to go through them, but I'm just going to explain that 10 centimeters, you need to convert that into meters. So you divide it by 100, 1.2 kilonewtons. So you need to times that by 1,000. So you'd have 1,200 newtons. And here you got 15 centimeters again. So 15 divided by 100, so 0.15 meters. And you've got this downloaded for your example. Now, when we say before, when we said a turning effect of a force, if I push from here, it will, and there's my pivot. In theory, this is spinning anti-clockwise. Now, what if instead I pushed from here? Then it'll spin this way, which is clockwise. Now, when you have moments, the sum of the anti-clockwise moment. But let me do this again, because based on what's already written there, I should do it according to that. So here, the sum of the anti-clockwise moment, so that's someone pushing down from there, that would spin it this way. So that's your anti-clockwise moment. So the anti-clockwise moment will be measured by the force of the person pushing it down multiplied by this distance from the pivot to where the force is. And if another person exerts a force here in such a way that the seesaw stays balanced in one place, then that means that distance from the pivot to that force, which makes it spin clockwise, it means that they're equal. So if someone sat on a seesaw, if the seesaw is at equilibrium, as in it's not one side's not higher, one side's not lower, it's just straight, then it means the anti-clockwise moment equals the clockwise moment. Now, what are levers? So levers are a simple machine consisting of a pivot, an effort, and a load. So look, if we apply an effort here, that just means force. You multiply that by the distance from the pivot to where the force is applied, and we have a moment. So this moment will go this way. That will cause this part here to also continue moving in the anti-clockwise direction and then cause the load to move. So what that means is we can make this part here much, much longer so that our moment is bigger. So that means a bigger moment is applied here with the same amount of force. Because you might only be you might only be able to apply a certain amount of force depending on your strength. But the longer you make this, the distance between the pivot and the force, the greater the overall moment that's being applied. So this is why we call this a machine. Now, gears. Gears are toothed wheels used with other axles at different speeds. As one gear turns, the other gear must also turn. Where the gears meet, the teeth both move in the same direction. So look, if I apply a force here, from here, the pivot's there, because that's where it's spinning from. To there, that we have a distance. That's going to create a moment. It's going to make it spin this way. When it spins that way, it's going to hit this part of the teeth here of this gear, and it's going to make it spin in the opposite direction, in the clockwise direction. Now, as this spins, it's going to connect on this, and that's going to make that spin in that direction. But the whole point here is this is going to provide a much larger moment, and that'll make everything else spin. And the same thing happens in gears in bikes. If the driven gear is made larger, it will rotate more slowly. So if your gear is really big, it will go around slower, 100%. It's going to go slower because it's bigger. Because look, the distance between the force and the pivot is bigger, but with a greater moment. Why does it have a greater moment? Because the distance between the pivot and where you're applying the force, so the force is the other way around. So let me just show that one more time. So here's your, actually I'll just show it here. So here, this is on the biggest gear. So that means if we're doing a downward force, your distance from the pivot to the force is larger. So overall, there's going to be a greater moment. But if you were to work out the circumference of that gear, it's going to be bigger. That means it's going to take longer for that gear to go around that bigger circumference. So if the driven gear is made smaller, it rotates more quickly, but with a smaller moment. So the forces acting on the teeth are identical for both gears, but the moments are different. So you can manipulate that. You can get the wheels to spin around faster, but you're still applying a greater as the same force. So if you use a larger gear, it goes slower, but it has a greater moment. So it can be, for example, easier. In that respect, it's more difficult to go uphill. You might want to go to a smaller gear where it's easy to spin it around. In the smaller gear, yeah, so a wheel in a bike is basically a gear. Yeah, so someone's mentioned here, this is a correct point. The wheel in the bike is a gear because the smaller gear turns the larger gear, the wheel, in other words. So what the gears do is eventually they spin the larger wheel. They both require the same force, but you just have to see, depending on what kind of terrain you're on, this is linked more to bikes with gears, mountain type bikes. So if you've got a larger, when you use a larger gear, you have a greater moment, but it spins more slowly. So you're not going to be riding the bike as fast. When you have a smaller gear, you've got a smaller moment, so you can't put as much force into it. Overall, the moment's not as big, but it spins faster. So it just depends on the situation. And this is what was linked to combined. How can we reduce unwanted energy transfers? So when we add oil or lubricants, it reduces friction between the surfaces. That means less friction means less thermal energy is lost. So surfaces will slide over each more smoothly less energy be wasted as heat. So the structure of the atom, this is something that we've already covered in chemistry, and you've covered lots and lots in paper one, but we'll quickly recap it anyway. Most of the mass of the atom is concentrated within the nucleus. And we know this because of Ernest Rutherford's experiments. The electrons are arranged at different distances from the nucleus, and they're in different energy levels. And we also know that atoms are neutral because they have the same number of protons and the same number of neutrons. And protons are positively charged, electrons are negatively charged, so they cancel each other out. And neutrons have an overall charge of 0. Now, electric circuit diagrams. What's the different symbols for electric circuit diagrams? So I'm gonna let you have a quick look at this. Now, you should know them, but it's not a big part of the exam. So you should know what an open switch looks like, a closed switch, the cell. The difference between a cell and a battery is if you have multiple cells, it becomes a battery. So a cell looks like this. If you've got two of them next to each other, then automatically it's become a battery. Then we've got a diode. A resistor is always a rectangle shape. So when you've got a variable resistor, you can see it's still a rectangle shape, but it just has the arrow going through it. A diode is a circle with a triangle and a line going through it. Now, when we say LED, which is a light emitting diode, it's the same shape as the diode. It just has the two little arrows added to it. So that's why even when you're talking about a thermistor is the same as a resistor, which is why you have that rectangle shape. An LDR is also a resistor, but a light dependent resistor. So again, you have that rectangle shape there. So these are ways just to help you memorize it. Okay, 10.3, series and parallel. Now, before I start talking about series and parallel circuits, let me just quickly recap. Not recap, but let me just summarize or explain what current, voltage, and resistance are. What I'm about to tell you, I'm probably going to say about 10 times throughout topic 10. But number 10, no, but initially let's start with current. So current, which is written as I, is the flow of electric charge. In other words, it's the flow of electrons around a circuit. So here's a circuit. Let me just get a different color. It's the flow of electrons throughout that circuit. Now it's measured in amperes. Now think of it like the flow of water in a pipe. So what we're saying here is the bigger the current, the more charge is flowing through per second. The bigger the current, the more water that's flowing through the pipe. That's how we look at current. So current is like the flow of water through a pipe. So if we increase the current, it means there's more electrons carrying even more charge per second. So from our analogy of the water pipe, it means more water is flowing through this pipe. Now let's look at potential difference, the voltage. Now voltage is the energy transferred per unit charge between 2 points in a circuit. So it's a comparison between, for example, let's say you've got your electrons on this right hand side here. They are flowing to the bulb. Yep. Now the bulb's going to make use of some of that charge. So the electrons that flow out from this side won't necessarily have the same amount of charge. So you have more charge on this side. You have more charge on this side, and you've got less charge on the other side. The difference between those two charges, so this half and the other half, is the potential difference. So when you work out the potential difference, you add a voltmeter in parallel. So that's a comparison between the charge flowing through this point here and the charge flowing through this point here. That's what voltage is, the potential difference. So it's like the pressure pushing water through a pipe. So we were talking about current being the water that's flowing through the pipe. The potential difference is like the push that pushes those electrons on through the pipe. The higher the voltage, the more energy each charge carries. In other words, the higher the voltage, the more energy, the more energy in each electron, the more charge in each electron. Now, some of that charge goes to the component. So you can imagine the amount of charge here is going to be high. So I'm pointing here. There's going to be more charge here. Now, that bulb, that filament lamp, is going to use some of that charge. So the charge on this side is going to be less. Potential difference is number one, take away number two. Point one, take away point two. Then we've got resistance, which is another key word that comes up a lot. That's measured in ohms, is written as an R. This is the measurement of how much a component opposes the flow of a current. So from an analogy perspective, you could say it's how much room the electrons have to move through. So you can think of it as, the water, if it's flowing through a narrow pipe and a large pipe, which one is the water going to flow through more easily? So the more resistance we have, the narrower the pipe becomes. So it makes it more difficult for the water to flow through. So the more resistance we have, the more difficult it becomes for the electrons to flow through the circuit. So I hope that makes sense. And then these three things are connected by this formula, V equals I R. Now when it comes up, I can go over this again. It's just overall, I know that this is just something that's not always well understood. So I wanted to start with it so we've got clarity. So what we're saying is current is the flow of electrons and they're carrying a charge. So that's a bit like the water flowing through pipes. The voltage is like the pressure pushing the water through the pipes. It compares the amount of charge. So when you add a voltmeter, it's always in parallel. So it compares it from one side to the other side. That's the potential difference. And then we've got resistance, which is like a narrow section, a narrow part of the pipe that slows the water down. So the greater the resistance, the harder it is for the current to flow. Okay, now we are talking about series and parallel circuits. So let me just get rid of all the previous stuff. So what are series and parallel circuits? There's two ways to connect the electrical components. You can connect it in series, where it's just one loop, or you can connect it in parallel, where you've got multiple loops. The thing with this multiple loop is, each loop is connected back to that same cell, that same battery. Now, certain circuits incorporate both series and parallel components. Okay, now in a series circuit, I'm going to read through what's on the board on the screen and then I will explain it in my own words in a bit more detail. Because for a series circuit, you need to understand about current, potential difference and resistance. And then we need to do the same thing for parallel if we're to understand this properly. So in each component in a series circuit experiences the same flow of current, meaning if I check the current here, if I check the current here, if I check the current here, the current will be the same throughout the whole circuit. So the current in series is the same everywhere. So the current is the same at every point in the circuit, as you can see. For example, if the current is 0.3 here near the battery, it's going to be 0.3 here near the bulb, 0.3 after the bulb. It's going to be 0.3 everywhere. So what we're saying here is the current is the flow of electrons through the wire. So and it's carrying charge and it's passing that charge onto components like this to make the bulb work, to turn the bulb on. So the electrons flow through the wire to um, make the bulb work. But the thing with current is, wherever you go in the circuit, the current will always be the same. Now, the next thing, I'm going to do this one first. The power supply's total potential difference is shared among the components. So we've done current. Now we're going to look at, so that's I. Now we're going to look at V, which is the potential difference. So the power supply's total potential difference is shared among the components. So what that means is the total voltage that's coming from here, so let's say that's 6 volts, is split across all components. Now this bulb here is identical to this bulb here. If they were different, the voltage can be split differently. But because it's the same bulb, it means this one gets 3 volts and this one gets 3 volts. Now, for resistance, the total resistance of two components is found by summing their individual resistance values. So the total resistance, whatever the resistance of this bulb is and this bulb is, that's going to be the total resistance of everything. So if bulb 1 is 5 ohms and bulb 2 is also 5 ohms, then what's the total resistance? It will be 10 ohms. So in a series circuit, the current stays the same. The resistance is the total of every single component's resistance added up, and the voltage is shared. The potential difference is shared among the components. Okay, so let's look at the next bit, parallel. So now in a parallel circuit, the voltage across each component remains consistent. That's because every branch gets the full voltage of the battery. Because look, this here is attached with its own loop there. This is also, in one respect, has its own loop with the battery as well. So if this is 6 volts, this bulb will get 6 volts and this bulb will get 6 volts. The current, now what happens with the current is, I'm just going to show you this here. Like we just said, what is current? It's the flow of electrons. So if you've got the flow of electrons happening here, got electrons flowing through, when it reaches this crossroad here, when it reaches this branching point, some electrons are going to go this way and some are going to go this way, depending on the resistance. Wherever there's more resistance, sorry, wherever there's less resistance, so let's say this is 3 ohms and let's say this is 6 ohms, the electrons will go in the direction where there's lower resistance. So that means you can have a higher current here flowing through this bulb than this bulb. Because the electrons always go in the direction where there's less resistance. Now, because the electrons, now let's look at the resistance part of this. The combined resistance of two resistors. So in series, you add them up, but in parallel, you don't. The combined resistance of two resistors is lower than that of the smallest resistor. So let's say this is 2 ohms and this is 5 ohms. The overall resistance is less than 2, is less than the smallest one. And why is that? Because resistance is resistance means stopping the electrons from flowing. But here, the electrons can go in 2 different directions. So it's easier for the electrons to flow. So adding more branches means it's easier for the current to flow. So that means the overall resistance will be less than 2 ohms. No, I've done that the wrong way. Sorry. No, that's right, isn't it? Resistance is smaller than 2 ohms. So in series, it's like you only have one pipe for the water to flow. So because there's only one pipe, all the current goes through that one pipe. That's why the current stays the same. But the potential difference is shared across different sections. Because the potential difference is the push, the pressure. So some of that pressure might go into one component, some of that pressure might go towards the other component. And here, if you have a blockage in the pipe, which represents the resistance, all these blockages get added up because they're all blocking the water from going back to the starting point. Now, if you're talking about parallel, in terms of current, it splits into branches. So that means the current also splits into different branches. Now, because each one has a separate loop going back to the battery or the power pack, the pressure is the same everywhere. So the voltage is the same everywhere. Now, if there's a blockage here, it's not going to impact the other loop. So that's why the overall resistance is less. So I hope that makes sense. That you need to get your head around completely. So in a series circuit, current stays the same. Voltage is shared. Resistance, you add them all up. In parallel, the voltage stays the same. The current is shared because it has multiple pathways. And instead the resistance is less than the smallest resistance. Okay, voltmeter and ammeter. How do we connect them? We connect them. A voltmeter is always connected in parallel, and I explained why. Because it compares the charge flow before the battery, so that's the amount of charge the electrons have before the battery, and the amount of charge the electrons have after they've gone through, not the battery, so the lamp, the bulb. So it compares the charge in the electrons before they go through the bulb and after they go through the bulb. Potential difference is the energy transferred per unit of charge that passes. So a volt is a joule per coulomb. And that can be calculated using this formula. Energy transferred equals charge times potential difference. So of course, you're going to be given this formula, but don't forget the units. Potential difference is in volts, joules, coulombs. Okay, an ammeter is always connected in series, like that. So voltmeter is connected in parallel, ammeters are connected in series. Okay, this does come up because you may have to draw a circuit. So make sure you know, make sure you remember. 10.8 current, the flow of electrical charge. So an electrical current is the rate of flow of charge in a circuit. So electrical current is the rate at which the electrons full of charge are flowing through the circuit. In an electric circuit, the metal conductors contain many charges that are free to move. Because it's made of metal wires, if you think back to chemistry, you've got your positive ions and you've got your delocalized electrons. So these delocalized electrons are what carry the charge. They're free to move around. When a circuit is made, the battery causes free charges to move. So that battery gives these electrons energy. So that battery's voltage, the potential difference. That gives the electrons the energy to move through that metal. It causes free charges to move. So it starts to move from one side, from the positively charged side to the negatively charged side. These charges are not used up, but they flow in a continuous loop. Okay, now there's a connection between charge and current. So charge flow equals current times time. In other words, the amount of current, the amount of charge, or the amount of current or charged particles going through a certain point within a certain amount of time. Again, you'll be given the formula, but please make sure you remember that current is amperes, time is in seconds, not milliseconds, and it's in charge flow is in coulombs, capital C. Okay, so here's a nice question. Can you tell me the answer in the chat box, please? I'm only going to give you guys about a minute. Okay, let's go through the answer. So the first thing we've got to do is we've got to convert 30 milliamps. And convert it back into amps. So that means we've got to do 30 divided by 1,000. So that should be 0.03 amps. This is why some of your answers were not correct, because you didn't convert the milliamps into amps. So you could divide by 1,000. Now we're using the formula Q equals IT. So what we're doing is 0.03 times 12,000. And let's do the maths. That equals 360 coulombs. Okay, let's do this one quick question quickly as well. So we've done 4 divided by 1,000. Because it's milliamps, we've got to convert it to amps. So we divided by 1,000. We've rearranged Q equals IT, so that T equals Q divided by I. So it's 0.04. Now, this is incorrect. What's written here? It should be 5 divided by 0.04, which gives us 1,250 seconds. Okay, closed circuits. So there will be a current in a circuit if the system is closed and there is a potential difference. So there will be a current in a circuit if the system is closed and if there is a potential difference. So let's break this down. Closed system, what does it mean? It means a complete circuit. Everything's connected There's no gaps, no breaks. And the switch is on, like this is, the switch is on. Now that's going to allow electrons to flow all the way around the circuit. Now, if there's a break in the switch, as in if there's a break in the circuit, or if the switch is off, the circuit is open, and now the current can reach here, the electron flow can reach here, but it can't get through that gap. Now, it said, and there's a potential difference. So what's the potential difference? The potential difference, like we said before, is the push from the battery. The battery or the power supply provides energy to push the electrons around the circuit. And we call that push potential difference or voltage. Now, if there's no potential difference, there's no reason for the electrons to move, even if the circuit is closed. So what we're saying is two things here. If you've got a loop like this, and this is a loop of wire, and it's completely closed, you've got electrons now, but the electrons won't flow unless you add a power supply. It's that voltage that causes the electrons to flow around that circuit. Now, if for whatever reason there's a break in that circuit, so we remove some of that circuit, now we've got a gap. Even if you have a voltage, the electrons are not going to flow past that point where the gap is. So what it's saying here is you need both. You need a closed circuit and you need a potential difference. Both go hand in hand. So for the current to flow, you need a closed circuit. In other words, a complete path without gaps and a potential difference. Okay, I hope that makes sense. Okay, conservation of current. At a junction of a circuit, at a junction of a circuit, current is conserved. Okay, now all this means is if I've got current flowing here, and we say, let's say it was 3 amps. Now that current, as we said before, at a parallel circuit is going to divide. Some of it's going to go this way, some's going to go this way. So the electrons are flowing through with the charge. When they recombine here, what's my current going to be there? Now, over here, it was 3 amps. So what's it going to be over here? Also 3 amps. Because the current that's split at this initial junction here, it recombines at this junction here. In other words, the current is conserved. So the amount of current that goes into the junction is the amount of current that comes out of the junction. So it's a little bit like saying, here I've got a pump. It pumps 3 liters of water. Some of that water flows this way. Some of the water flows this way. So when the pipes rejoin, here, how much water will we have? So we had 3 liters of water here. Some of the water's gone this way. So some of the water's gone this way. Some of the water's gone this way. How much water do we have at the end? It's still 3 liters because it's still part of the same system. So the current is conserved. Okay, variable resistors. What happens to current when resistance is increased? So when the resistance is high, it's harder for the electrons to move. So think back to what we said at the beginning of the session. What is resistance? Resistance is the ability of a circuit to slow in a sense, it's a blockage. So it's the ability to slow down the movement of the electrons. It's to slow down the current. So as the resistance gets higher, the current goes lower. So when resistance is high, it's harder for the electrons to move. That means the current will be lower. When resistance is low, it's easier for the currents to move. That means the currents will be higher. So a variable resistor, the way it works, it's able to change the resistance. So an example of a variable resistor in our homes would be a dimmer switch for the light bulb. So if anyone's got a dimmer switch for the light bulb, if you increase the resistance, that means you're reducing the flow of electrons going through the bulb. So what will happen to the light bulb? It will become dimmer. Now, if you reduce the resistance, if you make the resistance low, then more electrons will flow through and reach the bulb, and that will make the bulb brighter. So your dimmer switch controls the resistance. Okay, potential difference. So I know I've explained this before, but I want to explain it multiple times because it's these basics in this topic. It's the basics that aren't always understood, and if we understand the basics properly, it's going to really open up the topic. It's going to make it a lot easier for you to answer questions, and that's what we want. That's how we're going to get our grade 9s or grade 5s for those that are aiming for foundation. Because if you understand what I'm saying to you now, even from a foundation perspective, it makes the electricity questions so much easier. Please, please, please try as many electricity questions as you can after this session or when you next get the chance. I know I'm sure you've all been revising all day, and a 3-hour session of science is tiring. So I'm not expecting everyone to open up past papers straight away. But when you do, please try electricity practice questions and see how much you've understood. Just a little bit of practice helps, just so you can see if you've understood from the sessions. And that way, if you haven't, at least you can come back to me and ask. Now, what does current through a component depend on? The amount of current flowing through a component depends on the component's resistance. So the more resistance a component has, so for example, if this bulb's got lots of resistance, it's going to reduce the flow of electrons going through it. And also the current flowing through it also depends on the potential difference. So the current depends on both things. If the component has a higher resistance, the current will be smaller for the given potential difference. Now we need to know how these things connect. So potential difference, like we said before, is the push. This is the energy that pushes the electrons through the circuit. It comes from the battery or the power supply. The bigger the potential difference, the more the current will flow. But resistance is how much a component slows the current. So some components, the hotter they get, they move, the ions inside it move faster, so they reduce that means more electrons collide. So it slows down the current. So some components like resistors or thin wires, the same thing happens in thin wires. Thicker or wider wires allow for more current to flow through it. Same as a wide pipe would let more water flow through it. So the higher the resistance, the harder it is for the current to flow. And what connects these things together? Voltage equals current times resistance. So V equals IR. V is the potential difference is V. Now it says here voltage. That's actually, you can write voltage, but the more correct term would be potential difference, PD. And potential difference is measured in voltage. Current is measured in amperes, and resistance is measured in ohms. So in a given circuit, the larger the potential difference across the power supply, the bigger the current. Meaning if you've got a larger voltage coming from here, you have a bigger push on the electrons, so you end up having a bigger current. Components such as resistors and lamps, they increase the blockage. They resist the flow of charge through them, so they slow down the current. The resistance of connecting wires, now usually these wires don't have a massive resistance, so they get ignored. They do have an impact on the overall resistance, but we don't need to worry about that. They can be ignored. The larger the resistance in a given circuit, the smaller the current will be. So if we increase the voltage, the potential difference, we increase the current. But if we increase the resistance, we decrease the current. So let's have a quick go at this question. A filament lamp has a current of 600 milliamps. So what do we need to do here? 600 milliamps, we need to divide that by 1,000. So first things first, we've got to convert the units. And we know resistance is already 3 ohms. So we know the formula is V equals IR. So a filament lamp has a current of 0.6 amps. So that's 0.6 times the resistance, and its resistance is 3 ohms. Multiply them together. And has anyone got the answer there before me? The answer is 1.8 volts. So some example questions here for you to try. Well, one question there for you to try in your own time. Okay, so let's look at A and B. It says which circuit has the higher resistance and why. B has the higher resistance, and that's because it's got more components. And in a series circuit, you add up the resistance of all the components. So this wouldn't matter if it was a parallel circuit, but in a series circuit, you add up all the total resistance of each component. So here we've got more components in B, hence we have a overall higher resistance. Now, which circuit has a higher resistance this time? This time it's A, because when you've got a parallel circuit, the resistance is lower than the lowest resistance. So this is because in a parallel circuit, the resistance drops when there are more paths for the current to flow. So the current can flow in multiple pathways, and that means the overall resistance is less than the smallest resistance. So if that had a 2 ohm resistance and that had a 3 ohm resistance, the overall resistance of that circuit would be less than 2. Okay, A1 has a reading of 0.36 amps. So what would A2 have? That means A5 would also have had a reading of 0.36 amps. So we're trying to find out what A2, this one has. Now, because these bulbs are identical, they're going to take the same amount of current, but the current's going to still split down all three. So all we're doing here is 0.36 and we're dividing it by 3. So the answer is 0.12 amps. Okay, so those questions are there for you to try. You've all been given the resources, so please have a look through any remaining questions. And like I said, the more questions you do on calculation on electricity topic, the more solid you're going to make it for the exam. This is one of the topics where students lose a lot of marks. So you really want to get into the exam without losing those marks. Okay, 10.16 and 17 is linked to the core practical. So how can we determine the resistance of a component in a circuit? So that's what your circuit should look like. You've got a variable resistor just here. You've got your potential difference. You've got your voltmeter to measure the potential difference across the component that you're measuring the resistance for. So that's where your component goes. You put your voltmeter in parallel with it. So instead of that, you might decide to put a bulb, a filament lamp. Whatever you put there, you might put a motor. Whatever you put there, that's where you put your voltmeter in parallel to it, so you can find out your potential difference. Then to measure the current flowing through the circuit, you use an ammeter. The ammeter can go anywhere because the current's going to be the same throughout the whole circuit. Now, how can we investigate the current voltage characteristics of a resistor and any other component? So step one, set up the diagram as shown there. So now all we're doing initially is for a resistor, but we can swap this resistor out for any component. You can put an LDR, a thermistor, anything you want, and then you can make an IV characteristic graph. Now, the IV characteristic graph looks like this. Current on the y-axis and potential difference on the x-axis. Now, what we do here, step one, set up the equipment. Step two, record the current and the potential difference readings. Step three, modify the variable resistor 4 additional times, noting the new current and voltage. So you adjust your variable resistor on 4 or 5 different occasions, and you keep noting what the current is and what the voltage is. Then you reverse the connectivity. So that's here. You switch the batteries the other way around, reverse the connection on the battery leads so that both the ammeter and voltmeter display negative readings, because you want 4 positives and you want 4 negatives. So when you draw your graph, you've got in the positive quadrant and in the negative quadrant. Measure the current and voltage 5 times, making sure to adjust the variable resistor before each reading. So overall, you're doing 4 or 5 positive, 4 or 5 negative. Then finally, create the graph that displays the relationship between the current and the potential difference. In this case, what we've got is a straight line. Now, how can we do the same thing for a filament lamp? You do exactly the same thing. All we're doing is, if you think back, we had a resistor here before. We swapped that resistor for this bulb, for this filament lamp, and do exactly the same process. And that then gives us this IV characteristic graph. Now for different components, we'll get different graphs. So here you've got current and potential difference. This is for an ohmic conductor. So if something that follows Ohm's law, it means that as the potential difference increases, the current increases, as in they are directly proportional to each other. So when you have a straight line, that represents Ohm's law. That means you've got a component following Ohm's law. But the filament lamp doesn't follow Ohm's law, neither does the diode. But what you do need to do is be able to explain each IV IV characteristic graph. So let's start with this one. This is an ohmic conductor, so it follows Ohm's law. The current through an ohmic conductor is directly proportional to the potential difference. So an ohmic conductor is any component that follows Ohm's law. This means the resistance remains constant as the current changes. So what we're saying here is that every time the current increases, or the potential difference increases, the resistance stays consistent, because V equals IR. So R equals V divided by I. So at any point here, if we do V divided by I, V divided by I, V divided by I, because it's a straight line, resistance will equal the same. And you can check that in a question. if it's got numbers there, you can work out what R equals at any point, what resistance equals at any point, and you find the resistance at every single point will be exactly the same. Now, in a filament lamp, it's an ohmic conductor from a certain point to another certain point. After that, it kind of curves off. And that's because the longer you have a filament lamp on for, it's a little bit like having a TV on, or when you have a phone and you've been on the phone for a while, you start to feel it heat up. So components, when they're used for a certain amount of time, they start heating up. And if they heat up, the resistance increases. So look, the resistance of a filament lamp increases as the temperature of the filament lamp increases. This means the resistance is not constant as the current changes. Because what you've got to look at it is like this. Let's say you have positive ion within the metal wire or within the component, within the bulb itself. As it heats up, those positive ions move around more and more. The more they move, the more difficult it becomes, the bigger the blockage it becomes for that electron to flow through. So it becomes more and more difficult for that electron to get from one side to the other to carry the charge. So as something heats up, the resistance increases. The current at that point then, because if you look at this, the potential difference is still increasing here. But the current doesn't go beyond a certain point. That means it doesn't matter how much of a push is coming from the potential difference, the current won't increase beyond that point because the resistance has gone so high. Okay, now we have a diode. A diode flows in one direction only. So the diode has a very high resistance in the reverse direction. So in this direction here, the resistance is so high that the current is zero or close to zero. So the thing with the diode is it only allows current to flow in one direction. And that's why you've got this sudden, after a certain point of potential difference, you've got a sudden increase in current. Meaning the diode only allows the electrons to flow in that one direction. So the current through a diode flows in one direction only. The diode has a very high resistance in the reverse direction. Okay, so light-dependent resistors. What is an LDR and how does its resistance vary? So I'm just going to read through this and I'm going to explain it in my own words because it is a poorly understood topic. So the resistance of a light-dependent resistor lowers as light intensity increases. So as it gets brighter and brighter, resistance reduces. So in low light, the light-dependent resistor, the LDR, has a high resistance, which means you've got reduced current flow. Now, in bright light, a light-dependent resistor has a low resistance, which allows an increased current flow. So LDRs activate lights automatically in dark environments. Now, in my own, let me just so I can explain this in my own way. So at nighttime, when you've got low light, so what it's saying here, in low light, the LDR's resistance is high. Because resistance is high, less current flows through the LDR. That means more current flows through other parts of the circuit. In other words, through the lamp. So imagine you've got a circuit, and this is part of that circuit. You've got a circuit, and you've got your LDR. You've got a lamp as well. What we're saying here is that when it's dark, because it's dark, you have a really high resistance in here. That means less current flows through this part here because of the high resistance. So you have more current flowing. Now this, sorry, Just erase this 1 second and explain it again. I'm just going to do it like without the all the information there, so I can actually draw it out. So imagine you've got your parallel circuit, you've got an LDR here, and you've got a bulb here. Now the LDR detects that there's less light. So because there's less light flowing through it, what happens here? The resistance increases massively. So the current flowing through it decreases. Now if you've got less current flowing, if you've got less current flowing this way through the LDR, where's more of the current going to flow? Through the bulb. So that means this light brightens up and the light bulb turns on. Yeah, good question here. Do we need to know all the symbols? Yes, particularly these symbols, LDR, thermistor, because they're focused on so much, you need to know the symbol. Now, I hope that makes sense. Now, on a bright day, when it's bright, we just said the resistance decreases. So if the resistance decreases, you've now got more of the current flowing through here. And if we've got an increased current flowing through here, it means less of the current is flowing to the light bulb. So the light bulb turns off. So I hope that makes sense because, like I said, this is when it's taught in schools, it's just taught really quickly and it's not necessarily explained in much detail. And even if you look at this information, this is what you need to know from a GCSE perspective. And it really doesn't explain it because what it's saying is low light equals high. So it's dark. It's saying that it's high resistance. So it means less current flowing. So then why would the lights suddenly turn on then? That makes no sense. If the resistance is high, less current's going to get there. But what it means is less current's flowing through this. If less current's flowing through this, more current is flowing through the light bulb. Now, when it's bright light, the resistance decreases, so more current's flowing through this. More current is flowing through this, so now less is going to the light bulb, so light bulb turns off. Thermistors work in a similar way. The resistance of the thermistor diminishes as the temperature rises. So as it gets hotter and hotter, the thermistor can work in multiple ways actually. So the thermistor, apologies, there's some issues here. Okay, the resistance of a thermistor diminishes as the temperature rises. So the resistance decreases at higher temperatures. So if the temperature goes up, the resistance goes up. Now at high temperatures, a thermistor has low resistance. So at high temperature, sorry, I said diminish. I mean, that means diminishes meaning the resistance decreases. Sorry. So the resistance of a thermistor diminishes. The resistance decreases as the temperature rises. So at high temperatures, we've got a low resistance, meaning the current can flow through no problem. So what we're saying is, for example, you've got a high temperature, you have a low resistance. So that could mean that it allows more current to flow through, for example, a fan, and then that cools down the room. And at high temperatures, so it said exactly the same thing there. So thermistors are often used in thermostats. So in a thermostat, it works a little bit different. So when the temperature goes high, so in our house, the way a thermostat works is, so just excuse me 1 second. Okay, so the way a thermostat works in a house is, if the temperature goes too high, the heating gets turned off. So this is how this works in a similar way to what we just mentioned in the LDR. So when you've got a high temperature, the resistance decreases, so more of the current now flows through the thermistor, less goes into the heating system. So that means the heating turns off. Now, at a low temperature, the resistance is really high. So that means less of this current flows through the thermistor, more flows through the heating system, as into the thermostat, so the heating gets turned on. Okay, designs of circuits. How can we investigate the IV? So that's the current voltage variation in resistance in components such as diodes. So you arrange your equipment just like this. Now the thing with this whole experiment is you can do this experiment using any component. So you can swap that diode with absolutely anything. The main thing is that you have an ammeter in series and you've got a voltmeter in parallel. This resistor here is not needed, but this variable resistor is. So you arrange the equipment as so. Make sure you've got your power pack or battery attached. Now, note that the circuit is the same as any other one. So in the ones that come up, you can see more and more of these circuits. But instead of the diode, you could have a resistor or a filament lamp. Now, what you would do is, sorry, apologies, we already covered this yesterday, so it's fine. But you do exactly the same thing. So as we previously did yesterday, because we covered this, you keep with using the variable resistor, you change the resistance and you measure the voltage, the potential difference, and the current. And then you draw your graph for the diode. And what you'll find with the diode is it'll look like this. Okay, energy transfers. What happens to a resistor when a current passes through it? So when a current passes through a resistor, there is a transfer of energy. So this is what we covered yesterday. When a current passes through a resistor, so if you think back to yesterday, what is a current? It's the flow of charge. It's flow of charged particles, like it's the flow of electrons carrying charge. So every time they collide into something, they pass energy onto it. And that causes that thing to warm up. So when a current passes through a resistor, there's a transfer of energy. That causes the resistor to warm up. Now, what happens to the electrical energy when work is done in a circuit? Electrical energy is dissipated as thermal energy. So when you've got your electrons flowing through the circuit, when they collide with something, they pass on energy. So electrical energy is dissipated as thermal energy. So when an electrical current does work against the electrical resistance, meaning when you start increasing the voltage and you're pushing these electrons through the circuit, they're colliding with positive ions in the metal wire, and they're passing on energy. And that energy is then released as thermal energy. It dissipates, it's lost. So some energy is therefore lost. This is why a filament light bulb tends to get hot, because the more current that's flowing through it, the more energy that's being transferred. So the filament has a high resistance and lots of energy is transferred to thermal energy. So energy is transferred to thermal energy because there are collisions between electrons and the ions in the metallic lattice. So if you've got a wire and in a metal, if you think back to C1 chemistry, you've got metal ions, positive ions, and what is metallic bonding? You've got these positive ions and then you've got delocalized electrons which are free to carry the charge. Now, if this is that electron here has been has been pushed, given that push by the voltage by the battery, that electron's full of energy, charge, electrical charge. It collides into that positive ion, it passes the energy onto that ion. That ion gains in energy and will start vibrating faster. But now it's moving faster, it's going to cause even more resistance, even more of a blockage. So even more electrons collide with it, even more energy gets transferred, and then eventually that energy is released as heat, as thermal energy. So how can we reduce these energy transfers? Thicker wires could be used to reduce unwanted energy transfers. So it's a bit like using the analogy of the water pipe that we said yesterday. If you've got a narrow pipe, less water can go through. If you've got a really large pipe with a bigger lumen, a bigger gap, then more water will flow through. So thicker wires have lower resistance. This means that less thermal energy is transferred in the wires. So wider wires, thicker wires have less resistance. Heating effect on the circuit. So what are the advantages and disadvantages of the heating effect in circuits? Now, the only real advantage of resistance and causing this extra heat energy to be lost would be in a heater. So you could say a heater is quite efficient because even the extra heat energy that's being lost through the wires is a positive. It's something that we need. It's still going to emit heat, and that's the whole point of the heater. Now, disadvantages. Some of the energy is lost as heat, is wasted. The warmth produced can damage the insulating wires. It can pose a fire hazard. It can cause burns. So there's in any other mechanism, any other um, device other than heaters, it's a disadvantage. Now, what does the amount of energy an appliance transfer depend on? So energy equals power times time, or power equals energy divided by time, or power equals work done divided by time. So we have come across this formula before. Power in watts. And what is a watt? It is a joule per second. It's energy per second. Okay, I'm not going to go through this, but I am just going to remind that time has to be in seconds. So you have to convert the time into seconds. And joules are in joules, not kilojoules. So you have to convert the kilojoules into just joules. So you have to multiply by 1000. If anyone's struggling with the conversion of units, there is a 2 to 3 minute animation video on AMALearning YouTube channel. So I think it's topic, not I think, I know it's topic 1.3/1.4. So it is one of the older videos that we made. When I say older, we only made them in January. Okay, power is the energy transferred per second. It is measured in watts. So that's something we've already discussed. What is power? Power is the amount of energy transferred per second and it's measured in watts. Now, power of an appliance can be energy divided by time or work done divided by time. This is just a practice question. So again, I'm not going to go through it because I know everyone's maths is probably good enough to do this and basic algebra. If anyone wants me to go through it, I can, but you've got the resources. And afterwards, when you're going through this, you can pause on this and have a quick look through. So We know we've got to convert the 5 minutes into 300 seconds. And then it's just a matter of substituting the numbers, 750 and 300. Um, so energy equals power times time, and then just multiplying the two numbers. And we've got the energy. Again, here, we're trying to work out the time. So time equals energy divided by power. So we know our energy is 1.3 kilojoules, so we have to multiply that by 1,000. And that's why it's 1,300 divided by 1,200. Okay, the power transferred in a circuit device is determined by the potential difference across the circuit and the current in the circuit. In other words, power equals IV, current times voltage. So we can work out power with power equals. So now we've got power equals energy divided by time. We've got power equals work done divided by time. And here work done and energy are interchangeable. We've got power equals IV. Now, what does V equal? V equals IR. So if you swap that V with IR, then power equals I multiplied by IR, which is the same as I squared R. So that's where that comes from. So again, you will be given all of these formulas, but you need to make sure you are familiar with all of the units. Okay, domestic devices. So the amount of energy an appliance transfers is determined by both its power rating and the duration for which it is switched on. And that's something that we'll go through in a bit more detail towards the end of this topic. Okay, direct and alternating current. So this is an example of direct current. So direct current can either be, so the voltage in direct voltage or direct current is always constant. It can either be positive or negative. The current in the circuit is going to be direct. That's why it only shows one line. So whenever you see just one line, then you know it is direct current because it's only going in one direction. It's either positive or it's negative, and that's it. Now with alternating current, the voltage in alternating voltage is constantly changing. So what that means is every half turn, and we're going to learn a bit more about this in the motor effect. When the current's being made, every half turn, the the direction of flow of the charge changes. So that's why we get positive and then we get negative, positive, then negative. So alternating current just means it flows in both directions. So the voltage will periodically change from positive to negative and vice versa. And that means the current in the circuit is alternating. So it's almost like saying when you've got your circuit in direct current, everything just flows the same way. But in alternating current, that middle part there is initially it's this way, then it gets switched, and then it gets switched again, then it gets switched again. So that's constantly being switched with its feed. So it means the electrons are flowing this way, then they're flowing this way. They're flowing to this way, then they're flowing this way. They're flowing this way, then they're flowing this way. So that way, that's why you end up with a positive and a negative. And that means this is why the current will flow in both directions. It's alternating. Okay, so direct current is a current that passes through something in the same direction. So for example, the current produced by cells and batteries. That's why this was a bit of a bad example because you can't physically keep changing it. Whereas an alternating current, a current that changes directions, for example, the current in the national grid. So when the electricity is being produced in the national grid, and you're going to see this in more detail when we do the motor effect, because what you've got is a coil of wires spinning around a magnet, cutting a magnetic field. So when it spins in one direction, it's producing a current in one direction. When it's spinning back up again, it's producing a current in the opposite direction. So an electric current that regularly changes, so on an alternating current is an electric current is so an alternating current is an electric current that regularly changes its direction and size. So positive, negative, positive, negative. On a voltage time graph, this would appear as a curve alternating between positive and negative voltages. And the positive and negative values indicate the direction of current flow. So the current is flowing in one direction, then it's flowing the opposite direction. Now, in our domestic supply, our AC supply that comes from our local power plant has a frequency of 50 hertz. What that means is it alternates direction 50 times per second. And it has a potential difference of 230 volts. So it means it's going plus 230 minus 230 plus 230 minus 230. Now, so for example, right now I was charging my laptop. Alternating current would ruin my laptop. So what's coming when I plug my charger into the main supply, if my charger provided the main supply with a 50 hertz frequency, it would ruin the laptop. So what the charger, that part that's in the middle, what it does is it converts the alternating current into direct current. So the current only flows through the laptop in one direction. So we do have devices that do these conversions automatically for us. So live and neutral wires. Most electrical appliances connect to the mains using a 3-core cable. The insulation on each wire is color coded for straightforward identification. Okay, now there's one color on here which is incorrect. I just want to see if anyone knows which color is incorrect. But I can't even find the color. That seems to be close enough. Let's see if anyone has it right. Okay, I'll show you. The live wire should be brown. So the neutral wire is blue, the earth wire is green and yellow, but the live wire should be brown. Now, the live wire transmits an alternating current from the power supply. So it takes the current from the power supply and it sends it to the device at 230 volts. The neutral wire completes the electric circuit and is usually around 0 volts. And the earth wire provides safety by preventing the appliance from being electrically charged. So usually the earth wire is attached to the metal part and just in case it gets charged, it carries the charge away. So it's a safety mechanism. So why a live wire may be dangerous even when a switch is open. So a live wire can still be dangerous even with the switch open because it remains connected to the power source carrying voltage. So meaning even if you've got your kettle plugged in, as long as it's plugged in, it's still connected to the system. So live wire can still be dangerous even when the switch is open because it remains connected to the power source carrying voltage. So contact with it can still cause an electric shock. So this we've already discussed. Now, why is the live wire dangerous? Let's go through this in a. We've also discussed this. Now, why is it dangerous if a live wire and earth wire are connected? So a live wire and earth wire must never be connected to each other. This is because contact would create a complete circuit from the live circuit to the ground. And this may lead to electric shocks or fires. So the earth wire and the live wire are not it's done in a way that they don't come in contact with each other. Now here, it might seem like they're touching, but this is the insulating layer on the outside, so that's not a problem. Okay, power ratings. So what are domestic electrical appliances? So an object in the home is an object in the home that's designed to bring about energy transfers. So these are normal appliances that we have: washing machine, dryers, irons, coffee maker, microwave, kettle, toaster. Now, what does the amount of energy an appliance transfer depend on? The energy an appliance transfers depends on the power of the appliance and the time it is turned on for. So we're looking at power and we're looking at its time. And what does that give us? Energy. So it's a formula that we already understand. So so what is the relationship between power ratings for domestic electrical appliances and the changes in stored energy? So all electrical appliances transfer energy from one store to another. So let's look at this question again. What is the relationship between power rating for domestic electrical appliances and the changes in stored energy? So all electrical appliances transfer energy from one store to another. So for example, if it's got a battery, it's converting chemical into, it could be for movement. If it's a toy car, it could convert the chemical into kinetic. Um, the kettle converts the electrical energy coming from the main supply into thermal energy. Now, the higher the power rating of an appliance, the greater the transfer of energy in a fixed period of time. So the more, so if it says the appliance is 3 kWh, it means it transfers 3,000 watts of power per hour. So the first part of this topic is quite straightforward in that what are the poles of a magnet? So the places on a magnet where the magnetic forces are strongest are right by the poles. Wherever you can see there's more lines or magnetic field lines, that is an automatic indicator that you've got stronger magnetism or magnetic force there. So the places in a magnet where the magnetic forces are strongest, so two like poles will repel each other. Two unlike poles, or a positive and negative pole, will attract each other. So when two magnets are brought close together, they exert a force on each other. They either attract, there's either attraction or repulsion between the two magnets. And that's an example of a non-contact force. So that's something that you will have covered something that you already understand. So as this topic doesn't become difficult till we get to around 12.7, 12.8. So what are permanent magnets? A permanent magnet is made up of magnetic materials such as nickel, cobalt, and iron. Now it says steel here because steel is made of iron. So a permanent magnet always causes a force on other magnets or magnetic materials. And bar magnets and horseshoe magnets are an example of permanent magnets. And what are induced magnets? An induced magnet only becomes magnetized when placed in a magnetic field. So an induced magnet only becomes magnetized when it's placed in a magnetic field. So the magnetism is quickly lost when the magnet is removed from the magnetic field. So for example, if we have a permanent magnet, now that permanent magnet will have a magnetic field. So if something enters that permanent magnetic field, it experiences that magnetic field as well, but only if it's iron, cobalt, nickel, or if it's steel. Any other element won't experience it. So now if I get a steel paperclip or an iron paperclip, as soon as it enters the magnetic field, it becomes an induced magnet. If I put another paperclip, that becomes induced. If I put another one, it becomes induced, as long as it's within the magnetic field. The next one becomes induced until that weight is heavier, as in the downward force is heavier than the attraction force from the magnet. Then the paper clips will collapse. Now, at that point, when they collapse and fall, they're no longer in the magnetic field. In other words, they're down here somewhere. And because they're not in the magnetic field, they won't attract to each other anymore because the induction has gone. So the magnetism is quickly lost when they're removed from that magnetic field. So what uses do we have for induced magnets? So we can use induced magnets to sort metal waste. To sort metal waste, the magnet can become magnetized and attract metals. This can be moved by the magnet and deposited in a different container when the electromagnet is demagnetized. So this is talking about electromagnet. So electromagnet is where you have, for example, you have an iron core, so an iron rod. Around it, you have a coil of wire, and then these coils of wire are attached to a battery pack. Now, as soon as you turn the battery pack on, that magnet, this becomes a magnet. It becomes magnetized. It has a magnetic field. The second you turn it off, so you have a switch. As soon as you turn the switch, you open the switch, as in you turn it off, then the magnetism breaks away, as it is no longer magnetic anymore. So that's why magnets are really good, because they are, in a sense, temporary magnets. So as soon as you turn the electricity on, the electricity flows through it. When the electricity flows through it, whoops, when the electricity flows through it, when the electricity flows through, it becomes a magnet. When the electricity stops flowing through it, it stops being a magnet. So that means you can pick something up, like it's showing you here, it's picking it up, take it somewhere else, and then it can drop it because it turns the electromagnet off. Okay, so this is what I've already explained. Induced magnetism always causes a force of attraction. When removed from the magnetic field, an induced magnet loses most or all of its magnetism quickly. Permanent magnets do not lose their magnetism. So a permanent magnet is a material that produces its own magnetic field. An induced magnet is a material that becomes a magnet when it's placed in a magnetic field. So what is the shape of the magnetic field and how can we identify it, or how can we find out what it is? So The force between a magnet and a magnetic field is always one of attraction. So if we have a magnetic field, sorry, a magnet and a magnetic material is always one of attraction. So if I get iron, steel, cobalt, nickel, and I put them into this magnetic field, there's our paperclip again, it will be attracted to the magnet. The strength of the magnetic field depends on the distance from the magnet. So your strongest points are here, where the magnetic field lines are closer. But as the magnetic field lines start to have more and more distance between them, then the magnetic field at that point becomes weaker and weaker. So the magnetic field, we would feel it here and here, and it would be stronger. There'll be some, it would be part, it would be a little stronger along the sides there. But as you get further away, it would not be as strong as you're moving further away from it. Again, because the gap between the magnetic field lines becomes bigger. Now, the direction of the magnetic field at any point is given by the direction of the force that would act on another north pole placed at that point. So the direction of the magnetic field line is from north to south. So magnetic field always goes from north to south. Okay, now a compass also contains a small magnetic field. Because it's got a small bar magnet attached. A bar magnet is a permanent magnet, but it's only small. So that means if I got a large magnet like this, I could make that small bar magnet inside spin around in circles. So if I took my magnet and I spun it around, I could make that spin around in circles as well. So that bar magnet is going to be affected by anything with a magnetic field. So the reason we use the compass with a small bar magnet inside is because we use the Earth's magnetic field. So the Earth has a magnetic field. So the compass needle points in the direction of the Earth's magnetic field. So we always can work out which direction is north. The behavior of a compass proves that the Earth has a magnetic field. This means it must have a magnetic core. That indicates that the core of the Earth must be, or most likely is made of iron. We talk about Fe56. This is nothing that will come in your exam, but just a point that we talk about Fe56, but based on how P waves and well, how S waves, so how longitudinal waves after an earthquake, which is the S wave goes through a liquid and then goes through the core, and how they refract, it's most likely going to be heavier than Fe56. It's more likely going to be Fe57. So, plotting compasses. How can we plot a magnetic field of a magnet? This is more likely to come in a foundation, but it can come in higher as well. You place the magnet on a piece of paper and then draw around it. So we've drawn around our magnet. Now mark the north and south poles. So we've done that. Let me use a different color so it's more clear for you to see. So there's our north pole, there's our south pole, everything marked. Then we take our plotting compass, and what we do is at the whichever way the arrow is pointing, we put a little dot there. Then we put the compass after the dot. Whichever way the arrow is pointing, we put a dot. Where the dot is, you plot another compass, and whichever way the arrow is pointing, you put a dot. And you keep doing that until you've got all these dots, and you then join all the dots together, and that shows the magnetic field line. So this is exactly what it's saying here. Make a dot at the tip of the compass needle and then move the compass tail to this dot. Make another dot at the tip and repeat until the compass reaches the other pole of the magnet. Then you draw a line through the dots, so a little quick dot to dot, and add an arrow to show the direction of the field line. Then you just do the same thing from different points. So you might do it from here, from here, from here, from here, from here, to show all the different field lines that are there. Now, how does the behavior of compass prove that the core of the Earth is magnetic? So this is what we've already just covered. I'll just repeat it again anyway. When a plotting compass is placed in the Earth's magnetic field, the north pole of the compass will line up with the Earth's magnetic field lines and point to magnetic south. Now, what that means is if this is the Earth and this is the north of the Earth and this is the south of the Earth. Now, if we've got a compass, which way is our compass going to point based on when the lines go from north to south? So when lines go from north to south, sorry, in a magnet, the magnetic field is always north to south. So the lines are going to go upwards. So what they're going to do to our magnetic field, so now we bring our compass along, oops, and put our compass here, and actually let's put the compass here. Which way is our needle going to point? It's going to point upwards like that. Now we call that upward direction north. So we call it, so that's geographic north, as in that's our north pole. But actually, that's the magnetic south of the Earth. So let me explain that again. If you have your compass and it points this way, that means the magnetic field lines are also moving in the Earth, moving this way. Now, upwards on a compass, we call it north. But actually, which way does the magnetic field move? It goes from north to south. So when we look at a compass and we say, oh, that's north, actually what we're pointing to the direction of, we're pointing to the south, the southern direction of the Earth. So that is why we call it magnetic south. But us, geographically, we call it north. Sounds a little bit confusing, but it is what it is. So this proves that the Earth has a magnetic core. Okay, now this is where 12.7 onwards is where I'll read through what's on the slides, but then I'll explain it in my own words. So how are magnetic fields induced? So when current flows, through a conducting wire, a magnetic field is produced around the wire. Right, now I'm going to explain this. So what we just said is when current flows through a conducting wire. So first things first, what does that mean? Here's our wire, and it's metal wire, so it conducts electricity, and it's got electrons flowing through it. So we're saying it's got current flowing through it. Now, what do we mean by current flowing through it? When we say current flowing through it, think back to electricity, the topic. Current flowing through something means there's a flow of electrons or flow of charge going through that wire. Now, when that current flows through that wire, it creates a magnetic field around the wire. Creates a magnetic field around the wire. Now, that's an invisible field that can affect magnets or anything else that carries a current nearby. So that's when we say it has a magnetic field, it's a magnet. It has a magnetic field. So, and the magnetic field forms these concentric circles around the wire, like ripples in a pond. Okay, that's what this is saying here. Now, the direction of the current and magnetic field can be found using the right hand grip rule. So if you coil the fingers of the right hand as though you're holding the handlebars of a bicycle with the thumb pointing away from the hand. So like when you're in primary school, you said to someone, "You're my friend," and you give them a thumbs up. The thumb indicates the direction of the current and the fingers indicate the direction of the magnetic field. So you can see that these fingers are coiled this way and the thumb is pointing upwards. So the thumb pointing upwards tells you which way the current is flowing, and the direction of the fingers shows you the direction that the magnetic field is flowing from north to south. So when a current flows in a wire, it creates a circular magnetic field around the wire. If the direction of the current is reversed, meaning the person's thumb goes down and then you've got the hand, that means the current is flowing downwards and the magnetic field is going in the opposite direction. So the magnetic field will be in the opposite direction. It's been reversed. So that's all you got to do to reverse the magnetic field in this case. Okay, so the strength of the strength. So what actually affects the strength of the magnetic field? So one thing you can do is you can increase the current. So the current through the wire. And the more current that goes through the wire, um, the stronger the magnetic field. So you can increase the current through the wire. Also, the closer you are to the wire, the stronger the magnetic field. So you're going to feel the magnetic field stronger here than over here. So similar to a magnet. Because as you get further away, the gap between the concentric circles increases. So the magnetic field gets weaker. Now this fits in beautifully into the next topic, which is what is a solenoid? Now, a solenoid, in fact, what we should start with is this. So a solenoid is just a long coil of wire, like in a spring. It's made by wrapping the wire into loops. So you can see here, the wire has been wrapped into loops. Now, why do we need to shape that wire, or why do we need to put it into loops? So it says here, shaping a wire to form a solenoid increases the strength of the magnetic field created by a current through the wire. And it says the magnetic field inside the solenoid is strong and uniform. So let's understand these 2 points first. Why have we shaped it into these coils? And why does that cause a strength? Why does that increase the strength of the magnetic field? Now, if you just get a wire and you pass a current through it, automatically, what does it create? So when you pass current through a straight wire, it creates a magnetic field. The problem is that magnetic field is quite weak and it spreads out because you've got electrons flowing through the whole thing. So the magnetic field is spreading out, it's quite weak, it's not particularly strong. However, when you coil the wire into a solenoid, and remember, don't forget, what is a solenoid? Solenoid, it is just a coil of wire. That's a solenoid, it's just a coil of wire. All of a sudden, you could say something amazing happens. What happens is the magnetic field becomes stronger and more focused. So this is what this point is saying. Shaping the wire to form a solenoid increases the strength and the focus of the magnetic field created. Now, each loop of wire that's added makes the magnetic field stronger. So each loop of wire adds up with all the others. It makes the magnetic field much, much stronger than just if you had a single straight wire. Now let's understand this bit. The magnetic field inside a solenoid is strong and uniform. So the uniform magnetic field that's inside, so inside the solenoid, the magnetic fields are always, because it's circular and they're equidistant from each other. The magnetic field that forms on the inside ends up forming straight lines that are parallel and close to each other. Now, That means that the magnetic field inside is strong and is uniform, as in it's the same strength all the way through. So the field shape, now then it says the magnetic field around the solenoid has a similar shape to that of a bar magnet. So you know how a bar magnet has, let me erase some of these things so it's easy to see. So with a bar magnet, the magnetic field looks a bit like this. Well, with a solenoid, it looks exactly the same. So that's what this bit here means. The magnetic field around a solenoid has a similar shape to that of a bar magnet. Now, if you add a magnetic core to it, an iron core, so a magnetic material, which is iron core, it increases the strength of the magnet and the magnetic field of the solenoid. If anything, what you then, at that point, what you made is an electromagnet. So a solenoid is an electromagnet. So if you look at this here, if I put a magnet inside, if I put an iron core inside there, and if we attach this to a battery pack and we add a switch to it, when the switch is off, there's no current flowing through this wire. So it doesn't have a magnetic field. When you close this switch, so now the switch is closed. If I've done that really badly, let me erase that slightly. So if we close that switch, now we've got electricity flowing through. So as the electricity flows through, what does that mean? A magnetic field is made, which means, and you can strengthen it by putting your iron core inside, and it can now lift up any magnetic material. If I want it to stop, what do? I open my switch, and whatever's attached to my solenoid drops. So when I've got electricity flowing through this coil, is magnetic, so it picks up things. As soon as I close the switch, sorry, that's when when the switch is closed, I've got electricity flowing through the solenoid, so it turns into an electromagnet. It's picking up things. The second I open my switch, as soon as I open this switch, what happens? As soon as I open the switch, it means now electrons aren't flowing through it. It's no longer electromagnet. It's not got a magnetic field. So whatever's attached to it drops. So this is a solenoid is in fact an electromagnet. So we can use electromagnets for things like cranes, magnetic locks, like the ones that you might have in schools, electric bells, MRI scanners. So how can the strength of a solenoid be increased? Well, we can add a magnetic material such as an iron core into the center here, and that increases the strength of the magnetic field of the solenoid because this becomes this is magnetically induced, so it becomes an induced magnet, and it then also has a magnetic field which boosts the overall magnetism of it. So a solenoid with an iron core is known as an electromagnet. The other thing we can do to increase the strength of solenoid is increase the number of coils. Each coil is increasing the strength. So what can we use these electromagnets for? Electromagnets can be used to sort metal waste. The metal can become magnetized and attract the metal. This can then be moved by the magnet and deposited in a different container when the electromagnet is demagnetized. So this magnet here, it will be attached to a battery. And if you remove the battery or you close it, when you attach it to a battery, if you close the switch, I've not drawn this very well because it's not showing the image. Let me just start this again. So let's just put that here. This is our contraption. It picks up metals. As long as the switch is closed, it's got electricity flowing through it. It's flowing through the coil of wires. So you've got coil of wires inside it. It's got the iron core as well, which becomes an induced magnet. They've all got a magnetic field that causes it to pick things up. As soon as you open the switch, what happens? You've the circuit is incomplete. So all the things that have been picked up get dropped. Now, just quickly recap this then. Just having a coil of wire, if you have a coil of wire, so just having a coil of wire, what will that do? That creates a magnetic field, just having a coil of wire. So if I have this coil of wire and if electricity current is flowing through it, it becomes a magnet. So let me just rub all these things out and let's quickly recap this. Let's fully understand it. And we'll move on to the next bit. So we've got our coil of wire and that's linked to our complete circuit. So as long as electricity and as long as current's flowing through it, this has the same, this is a magnet because it has, as long as current's flowing through it, it's a magnet. Just a coil of wire is a magnet. It's like an induced magnet. We call it electromagnet because it's got electricity flowing through it and it's a magnet because it has a magnetic field, particularly through the center of it. Now, how can we make that magnetic field stronger? You can have more coils of wire, or in the center of it, you can add an iron core. You could use a cobalt, you could use nickel, but iron is what they usually use because cobalt and nickel aren't usually used in this way. And that just makes it stronger because the wire is magnetic. So if we think back to permanent magnets and induced magnets, how does an induced magnet get formed? This solenoid has a magnetic field. If I put a magnet inside it, that magnet is now has been put into that magnetic field. So it now also has a magnetic field. So you've doubled up the magnetic field. You made the magnetic field stronger. Okay, there was a question here, but I believe I've answered that question now. The question was, is it just iron that makes the electromagnet? So as I've just explained, it's the solenoid, as in the coil of wire that becomes the electromagnet. Adding the iron just strengthens the magnetism. And when you turn the current off, you stop providing the current, as in turn the electricity off, then you demagnetize it. Okay, so here we are coming up to Fleming's left-hand rule. So a current carrying conductor, when placed near a magnet, experiences a force. So what this means is, here's your two magnets. We have a magnetic field going from north to south. And this thing here is represents a coil of wire. So let me do my own version. So if that's the North Pole and that's the South Pole, in between what we've got is a magnetic field. I mean the North and South Pole of a magnet. So in between, we've got a magnetic field. If you now put, if you now get a wire and that wire has, so we're talking about a current carrying conductor. So a metal wire, if you put a metal wire, but and that metal wire has current flowing through it, if that wire with current flowing through it breaks the magnetic field, then that wire will move. So it will experience a force. Because what happens is there's an interaction between the current, because when you have a current flowing through a wire, it produces a magnetic field. So this wire here is producing a magnetic field. When you've got going from north to south, that's also a magnetic field. So these two magnetic fields interact with each other, and what happens? The wire moves. The same way when you've got north and north, they repel each other. That's what's happening here. The two wires, the magnetic fields have interacted with each other, and the wires moved. So the magnetic forces occur due to the interaction between magnetic fields. And how a better way of understanding that is with, I mean, this whole thing is called the motor effect. So if you get two magnets, north, south, that's got a magnetic field. If you cut the magnetic field with a wire, and you just put a wire in there with a current going through it, then the when the current goes through a wire, it creates a magnetic field. We already have a magnetic field between the magnets, and so they interact with each other. And that interaction causes the wire to move. Now that's the motor effect. Because if you can get that wire to move, essentially what you're doing, you are causing movement. So you can cause a wheel to move and make a car move. You can make the blade in the blender to move. You can make the what you call the helicopter, the blades of the helicopter to spin, to move. So that's the motor effect. So I'm going to read this out and I'm going to explain this in my own words in a bit more detail. So when a conductor carrying a current, so when we say conductor carrying current, what do we mean? We just mean a wire. We're talking about this. When a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. So essentially what's being said there is what I've just said with that diagram. So, and what Fleming's left-hand rule does, it represents the relative orientation of the force. So it's telling you if the force is going to move, is the wire going to move upwards, is the wire going to move downwards, left or right. So the current in the conductor and the magnetic field, depending on which way they're flowing, it indicates which way it's going to move. So if you get your hand in this formation here, where you've got a right angle between your thumb and your first finger, and you're a right angle between your first finger and second finger, your first finger represents the force, as in the movement, direction the wire moves. So remember this as FBI. Your first finger is B, which if you look at this formula, this formula here, B is magnetic flux density, in other words, the magnetic field. And I, as we already know, is the current, which is the second finger. So I'll repeat this one more time. So what is Fleming's left-hand rule? Fleming's left-hand rule helps you predict the direction of the force on a wire carrying current inside a magnetic field. So let's look at it like this. We've got magnetic field, north to south. So magnetic field is going this way. So if we've got the hand, our magnetic field is going that way. That's our first finger. So our first finger should point that way. And we put a wire in that magnetic field with the current coming towards you. So now your second finger is pointing towards you. Your first finger is going left to right. And which way is your thumb pointing? Upwards. So that means this whole wire is going to move upwards because of the interaction between the current in the wire and the magnets. So we've got a current flowing through the wire. We've got that wire placed inside the magnetic field. And what does that do? It produces a force. So that wire moves. That movement in the wire, that's what we mean by motor effect. Now, the easiest way to memorize this is FBI. Okay, so in what direction do you position the middle and the index finger? So I'm pointing the index finger in the direction of the magnetic field, point it from north to south pole. So this is your index finger, the first finger. So your first finger always goes from the north pole, the north part of the magnet, to the south part of the magnet. When you're looking at the middle finger, you point it in the direction of the current. Remember that current flows from the negative, from the positive terminal to the negative. So your second finger, your first finger is north to south, and your second finger is from south to north. But they will all most likely in your exam questions, they will already tell you they will already give you arrows giving directions. Okay, magnetic flux. So this is a new formula that a lot of you might have well, everyone will have covered it, but you might not be as familiar with it because the word magnetic flux density only comes in this one formula at GCSE. As per usual, you will be given a formula booklet, so you'll have this formula in that booklet. However, make sure you know the units. So force is newtons, length is in meters, current is in amperes, and magnetic flux density is in Tesla. But this is the type of Tesla that you don't need to boycott. So you can still write in the exam and not feel too guilty. Well, shouldn't feel any guilt at all. Okay, so let's have a quick go at this question. Calculate the force. So force equals Bill. B is magnetic flux density, so we know what B is. It's 2 Teslas. So we can add that in, 2. We know what the current is. It's 2.5, so we can write 2.5. And our length is 45 centimeters, so we need to divide that by 100. So we get 0.45 meters. And then multiply them together, and you now have your force. 2.25 newtons. And you've got lots of practice here to go through prior to the exam. And when we go through the math section of our pre-exam workshop, masterclass, there'll be lots of questions like this as well for us to practice. Okay, now moving on to 12.14p, which is the last part of this. Okay, so now that we're at 12.14p, this is triple. Yeah, so this is 12.14p, this is triple only. So 12.14p, the motor effect, is a triple only topic. And again, now that you've understood the motor effect, this whole topic becomes a lot easier. It's a lot easier to understand. So it says how does an electric motor work? A simple electric motor can be built using a coil of wire that's free to rotate between two opposite magnetic poles. When electric current flows through the coil experiences a force and moves. So an electric motor is a device that has a coil of wire carrying a magnetic field that tends to rotate. So let's just quickly go through this. I mean, I'm going to explain this in my own words. And essentially, I'm just going to repeat everything I said for motor effect and connect it to this. So, because what we're actually saying here is that how can we make an electric motor? An electric motor spins, as it spins, it can be used to make something else spin. So if anyone's ever seen a motor, it's just something that spins. So if you attach a wheel to the motor, the wheel will move, will spin. Whatever you attach to it, it'll spin it, it'll make it move. So an electric motor, what it's doing is it's converting electrical energy and it's converting it to kinetic. So the electric motor converts electric energy into kinetic energy. So let's break it down into a bit more detail. Now, electric motor is made up of a coil of wire. So you have to look at this as your coil, as the coil of wire. It's got magnets. So you've got your north pole there, south pole there, and it's showing the magnetic field going from north to south. And it's got a commutator. Now, you don't really need to know too much about the commutator itself. It just keeps the coil spinning in one direction. Now, what happens when the current flows? So what we've got here now is the current flowing. We can see, let's look at, let me highlight it for ease. Let's look at this half first. Our current is flowing this way. So your first finger, your second finger should be pointing that way. Your magnetic field is moving left to right. So which way is your thumb pointing? You can answer if you're able to answer quickly. Which way is your thumb pointing? Let's have a look. So let's try this. So essentially what's happening is our current is going that not upwards, but this means it's going towards the screen. So your first finger should be pointing towards the screen. Your first finger is pointing left to right. So that means, so if you get your two fingers, those first two, the second finger pointing towards the screen, get your first finger pointing left to right, and then your thumb will point downwards. So that half is pointing downwards. Now, when you go to the other half, so now we're looking at this half here. What's happening this time? This time the current is coming out of the screen. So your second finger is pointing towards you. Your first finger is going left to right. So that means your thumb is pointing upwards. So now your thumb is pointing upwards. So this finger that I'm trying, well, that's showing the current. So that's your second finger. So let's do it as F, B, I. So this finger, the I finger is pointing towards you. The B finger, which is the magnetic field, is pointing left to right. And that means your thumb should be pointing upwards. So this part is moving upwards. So in other words, we're causing it to spin. Naturally, it's just going to spin. And that spinning is what the electric motor is. So the coil carries electric current. The coil is sitting in a magnetic field. Now, what have we said? When a coil has current inside it and it's sitting inside a magnetic field, what does that produce? it creates a force. So that means the coil in one half moves downwards, and in the other half it moves upwards. So because the forces are in opposite directions on each side, one side goes down, one side moves up, and that causes that coil to rotate. Now, why does the coil keep spinning? Because as it spins, what the commutator does is it makes sure that the current reverses direction every half turn. In fact, I won't go into too much detail about this because I don't think you need to know. Okay, and actually it explains it here. This makes sure, so what does a split ring do? This is the split ring commutator. What it does is it reverses the direction of the current every half turn. So at the moment you've got the current going this way, and then once it's gone half a turn, it's going this way. Because it's making it go in opposite directions, it means one half of that coil is going to go downwards, move downwards, and the other half is going to move upwards. So this makes sure, what does the split ring commutator do? It makes sure that the current in each side of the coil of the wire is going in the same direction. This means that the force continues to act downwards on one side and upwards on the other. So it reverses the direction of the current each half turn. This keeps the forces acting in the same way on each side. So the coil keeps spinning in the same direction. The main thing to understand here is, what does the coil keep doing? It keeps spinning. Now, that spinning is how an electric motor works. That's the motor effect. So that can now be used in it can be used to turn a wheel. It can be used to turn the blade in a blender. It can be used for lots of different things. So look, how can the direction in which a motor spins be changed? You can either change the direction of the magnets. So if this becomes south and this becomes north, then our magnetic field is going to go the other way. So you know how this is spinning this way? It'll stop spinning that way and it'll spin the other way instead. Or you can change the direction of the current. So at the moment, the current is going this direction. If instead you reverse the current, because you can swap around this battery, so the positive ends there, the negative ends there, and that way the current will flow in the opposite direction, and that will also make it spin the other way. Now, how can the speed in which the motor spins be increased? You can increase the strength of the magnet. Now, this one here, even if that information wasn't there, we can work out, because what makes it spin in the first place is the interaction between the magnet and the current. Now, why am I putting a circle around the battery that provides a potential difference of voltage? Because the bigger the voltage, the bigger the push on the electrons, the bigger the current. So if you increase the number of batteries, the number of cells, and as in you make it a stronger battery, or use a power pack and use a stronger voltage, stronger potential difference, that will increase the current. Or you can use stronger magnets. So if you use stronger magnets, then it will spin faster. If you use a stronger current or increase the current, the speed will increase as well. 13.2 is for everyone, and then 13.3 is triple only as well. So there are a few parts of this topic which are triple only and combined as well. So it's a mix between the two. So with 13.1, a lot of this links to what we learned about yesterday. So what we're looking at here is how the generator effect actually occurs. So I'm going to read through everything, then I'm going to explain it as well. So if an electrical conductor moves relative to a magnetic field, or if there's a charge in the magnetic field around a conductor, a potential difference is induced across the ends of the conductor. If the conductor is part of the complete circuit, a current is induced in the conductors, right? So let's explain this one step at a time. So Firstly, the generator effect is how we produce electricity using movement and magnetism. If we go back to Fleming's left-hand rule, we spoke about F, B, I. So we said force, magnetic field, and current. Now, if we've got two of them, we automatically generate the third. So what we're saying here is we are making electricity. So if you spin, if you, for example, attach these slip rings to a wind turbine, when that wind turbine spins, it's going to spin this coil. And when that coil spins, that means we have force. We've got that movement. And it's in between a magnetic field because there's your north magnet, your south side magnet. And because you've got this movement in between the two, what are you automatically creating? A current. So when a wire moves through a magnetic field, or the magnetic field changes around the wire, because we could equally, when this wind turbine spins, we could just get the magnets to spin instead. That will do the same thing. When that happens, a potential difference is created across the ends of the wire. What that means is, within that wire, we are creating a potential difference. And what does the potential difference do? It's the push on the electrons. And current is the flow of electrons. So the bigger the potential difference, the more the electrons are going to flow around that coil. So if the wire is part of a complete circuit, as it is here, because you can see it's attached to a bulb, then a current is produced and the current will flow and the light bulb will turn on. This is how we generate electricity. So in power stations, wind turbines, bike dynamos, etc. So let's look at this step by step. The wire or coil, so let me just highlight that. This is the wire, that's the wire or coil. It moves through the magnetic field. So if we attach this to, whoops, it's a different pen, to our wind turbine. The wind turbine is causing our coil to rotate. Now, the motion, that movement, what's happening? It's causing the coil to break the magnetic field. When it breaks the magnetic field, it creates a potential difference, which causes electrons to start moving faster through the wires. In other words, it creates a current. In other words, electricity has been generated. That's why we call this the generator effect. So an induced current generates a magnetic field that opposes the original change, either the movement of the conductor or the change in magnetic field. So all it's saying here is that we can either get this bit to spin or we can even get the magnet to spin. Either way, as long as you get the wire to cut across the magnetic field, you are generating current or electricity. Okay, now this is 13.2, so this is for everyone. What affects the direction? What affects the direction of the induced potential difference or current? So the direction of the induced potential difference and therefore the induced current depends on two main things. Either the direction of movement, so it could be if you move the wire or the magnet in one direction, actually the best thing to show you here. So look, on this diagram here, we're saying the coil is being spun that way. Yeah. Now let's look at, I'm going to highlight the left-handed side. Let's look at the left-hand side. So what we're saying is, and let's look at this from a Fleming's left-hand rule perspective. We're saying we're causing it to move upwards. So if you put from your left hand, if you have your thumb facing upwards, so thumb facing upwards, and we have our first finger magnetic field. The magnetic field is going across that way, so that's going to be that way. And that means the current should be coming out through the screen. So the current, although it shows it actually incorrectly on there, the current should be going that way. Now, if we rotate it the other way around, so as in we're rotating it this downwards. So now if it's the forced thumb should now be pointing downwards. The magnetic field is going from left to right, from north to south. And our current, which way is our second finger pointing? It's pointing towards the screen. So this current there should be pointing that way, not the way that's on there. Now we can cause the switch in the direction it moves by moving the magnet, or we can move the coil itself. Either way will create electricity, current. Now what affects the size of the induced potential difference or current? We can increase the speed of the movement. So if we move the turbine, the wind turbine or whatever turbine it is, faster, then we increase the current. We can increase the number of coils or turns of number of turns of the coil. So that shows the coil being rotated, but the turns of wire on that coil, we can add more coils overall. Or we can increase the magnetic field strength. So if we increase the magnet, now when we're talking about this whole topic, everything always goes back to F, B, and I. So if you want to increase the force, you make it move faster. If you want to increase the magnetic field, so the other thing, you can increase the force by increasing the speed. You can increase the magnetic field by using stronger magnets, and you can increase the current by using more coils of wire. Okay, 13.3p, this alternators and dynamo. So this is something which is linked purely to triple. And then as you can see here, 13.4 is triple as well. And then we go on to 13.5, which is for both. Okay, so how can we generate alternating current? The generator effect is used in an alternator to generate alternating current, and in a dynamo to generate direct current. So in alternating current, what this actually means is the coil moves through the magnetic field, and the coil cuts the magnetic field lines. So the magnetic field line, it shows which way it's going. A potential difference is induced across the coil. This is a complete circuit, so current is induced in the coil. Every half turn, the potential difference reverses direction. So every half turn, the current changes direction. So what this means is, for example, again, what we just showed a bit ago, let's say the red part of this coil is being moved. Actually, let's use this rotation here. It means the red part is going downwards. So now if you use your Fleming's left-hand rule, if your thumb is pointing down, magnetic field, so your first finger is going from left to right, that means your current is flowing towards the screen. In other words, the current is going this way. Now, that same red part, when it gets to the top over here and starts spinning downwards, sorry, at the moment it's spinning downwards. So when it gets over here, down here, and it starts spinning upwards, now your thumb needs, from a Fleming's left-hand rule perspective, your thumb has to point upwards. Your first finger is going from left to right. So that means now the current should be coming out of the screen. So the current is now flowing this way. So every half turn, the direction of the potential difference switches, and the direction of the current switches. In other words, the current is going in one direction for half a spin, half a turn, and it's going in the other direction for the other half of the spin. So that's why we call it alternating current, because the current's going in both directions. Now, how can we generate a direct current? So direct current's a little bit different. It has something called a split ring commutator. Now, the way the split ring commutator works is that in a generator, we already know that we can produce alternating current, but in a dynamo, we still use the same principle. You've got that coil that's rotating, and it's rotating within that magnetic field. But what we do is we use that split ring commutator to change the coil's connections every half turn. What that means is, if you look really carefully there, you'll see a positive charge and a negative charge. If I zoom into it, there, you can see a positive charge and a negative charge. So what's happening is every turn, so let's say it's spinning and the current is flowing this way. Now, if this is alternating current, on the other side, this is going to spin that way. But what happens is when this part of the current, for example, let's say this part here is spinning upwards, when it reaches the top and it starts to spin downwards, this changes. It turns this into a positive and this into a negative. So the current continues to flow in the same direction because it's reversed the flow. So let me explain that step by step. The coil spins inside the magnetic field. As it spins, the coil cuts through the magnetic field lines. And if it's cutting through magnetic field lines, that's inducing a potential difference. And because we've got a complete circuit here, what else are we doing? We are inducing the flow of current. Now, without help, let's say we didn't do anything here, every half turn, what happens? The voltage changes direction. So the current changes direction. But what the dynamo does every half turn, it's a really clever device. It switches the connections of the coil every half turn. So it switches the direction. It switches the connection, sorry. So just as the voltage is about to reverse its direction, the ring flips everything. So it continues going in the same direction. So even though the coil's voltage is about to reverse, the split ring commutator flips the wires at the same time. So the current in the external circuit always flows in the same direction. So this is direct current. But the principle is the same. It always goes back to FBI. You've got your force that's moving the coil. We've got a magnetic field. So if you've got F and B, automatically that produces a current within the wire. Okay, microphones and headphones. So let's start with headphones. So loudspeakers and headphones turn electrical signals into sound. So loudspeakers and headphones use the motor effect to convert variations in current in electrical circuits to pressure variation in sound waves. Now I'm going to explain this in a bit more detail. But what we're saying is, think back to what the motor effect is. It's what we covered yesterday. If you've got a magnetic field and your magnetic field goes from north to south, if you place a wire in that magnetic field, if a current flows through, sorry, if that wire, um, if that particular wire now moves, no, sorry, yeah, so let me start again. You've got a magnetic field there. If electrical current flows through this wire, the magnetic field and the current interact with each other. And what does that lead to? It leads to movement. So that wire then moves. So what we're saying here is that a varying current flows through the coil. That varying currents come from the microphone. Now, the electrical signal from the music that person listening to or the voice or whatever it is not going to be constant. They change rapidly. So I'm speaking right now. I might speak a little bit louder. I might speak a little bit quieter. I might not speak at all. So at each point, what's happening with this microphone is making variation in the electricity that's being produced. That electrical current is flowing through this wire in variations. When that electrical current cuts across the magnetic field, it causes that wire to move. Now this wire is attached. So you've got your magnetic field, you've got your wire, and the wire itself is attached to a speaker cone. So let's look at this. Let's look through this and let's make sense of it. A varying current is flowing through this wire. So these signals pass through the coil of wire inside the speaker. The coil is sitting in a magnetic field. So there's a magnetic field going from north to south. Now, whenever the current flows, what happens between the magnetic field and the current in the wire? Because if you have a current flowing through a wire, it also has a magnetic field. The magnetic fields interact and it causes the wire to move. Now, that means the wire starts to move back and forth. Now, the coil or this wire is attached to a cone, like a piece of material. And that causes that cone to vibrate. And it moves when it vibrates and moves, it makes the cone move back and forth. So if anyone's ever looked at speakers close up, you see these cones moving up and down. That's what's happening here. Now, when the cone moves, the vibrating cone causes the air particles to vibrate and move as well. And it pushes the air molecules back and forth. And it creates a longitudinal sound wave. And therefore, you hear sound. And this would be the same for any wired headphones, any headphone. However it works. This is how headphones work. Now let's look at microphones. So microphones use the generator effect. So the motor effect is when the wire moves. So keep this in mind. The motor effect is, so for the headphones to work, it's the motor effect. The motor effect is where you have a current. So in FBI, it's when you've got the current and you've got the magnetic field and you have the current. So it produces a movement. But in the microphones, it uses the generator effect. So from FBI, this time we've got the force, we've got the magnetic field, so we're producing a current. Now, really I should have switched this around, but it's fine. Microphones use the generator effect to convert pressure variations in sound waves into variations in current in the electrical circuit. So this is now the other way around. Here's your cone. The cone has like a diaphragm, which is like a thin layer of material that's attached to a wire. The wire has a magnetic field. Now, as we speak into this cone, into this microphone, so what I'm trying to represent here is the microphone. As we speak into it, the cone vibrates. The diaphragm vibrates. It's a thin sheet inside this cone. It vibrates. When it vibrates, it causes this metal, this conducting wire full of electrons to vibrate. Now it moves. Now where's that movement happening? So that's a force. Where's it moving? It's happening in between within this magnetic field. Now, if you get that movement within a magnetic field, what does it produce? It produces a current. If anything, it produces a varying current. Now that current starts flowing. that current can go to someone's headphones, and in the headphones it converts the current into movement, and it causes the movement in the cone to make a sound. So these things go hand in hand, except here we have the generator effect, and here, so here we have the generator effect, and in the headphones we have the motor effect. Okay, 13.5. So we're back to a topic that is for everyone again. So transformers. What are transformers? So here we've got our primary coil, our turns of wire, and because we have electricity flowing through it, we've got current flowing through it, it induces magnetism within this iron core. When that induced magnetism reaches this next set of wires, that means the wires cut a magnetic field and current is induced here in the secondary coil. So we've got our primary coil, which induces magnetism within the iron core, and that induces that magnetic field is cut by these wires, so that produces current and voltage in the secondary coil. So we might start here with 6 volts, but if we have twice the number of coils here, then it'll convert it to 12 volts. So this is a step-up transformer. So the ratio of potential difference across the primary and secondary coils of the transformer depends on the ratio of the number of turns on each coil. So what we showed here was, let's say you've got 10 coils here. Over here we'd have 20 coils. So because the number of coils is doubled, the voltage will also double. So the alternator, this is how it works, which is what I've just explained. We've got our core, which is made of iron. The alternating current in the primary coil produces a changing magnetic field in the core. This induces an alternating potential difference across the secondary coil. So when current flows through this one, what happens? It induces a magnetic field in this core. That induces a potential difference across these wires on this side. In other words, it creates a current on this side. So step-up transformers have more loops on the secondary coil, so voltage is increased. And a step-down transformer have fewer loops on the secondary coil, so the voltage is decreased. Now this is specifically for triple. If transformers were 100% efficient, the electrical power output would equal the electrical power input. So you can do this as a ratio. The voltage of the primary input divided by the voltage of the secondary input is equal to the number of turns on the primary divided by the number of turns on the secondary. So this is a practice question for you to have a go at. And lots of practice questions here for you to have a try at. But past paper practice is essential here. Very, very important. Okay, 13.8 and 13.9, which is the national grid. So what is the potential difference and frequency of electricity in the UK? So in the UK, the primary electricity supply is alternating current. Now it operates at a frequency of 50 hertz. What that means is the current flows in one direction, then it flows in the other direction, and it switches from one to the other 50 times per second. And the potential difference of the electricity coming out is 230 volts. So the national grid, the electricity is conveyed from power stations to consumers through the national grid. Which is a network of cables and transformers that connects power stations to the consumer. So we have our main power station, then it's sent to a secondary power station before it's sent to our homes. Now this would be a step-up transformer because it increases the voltage massively, and then afterwards it's decreased again to make it safe for our homes. And I will explain why that is the case. as well. So what is the national grid? Step-down transformers are utilized to significantly reduce the potential difference. This increases the safety. So usually at the step-up transformer, the voltage is increased up to 400,000 volts. Now that's because power equals IV. So if we increase V, we can decrease I. Now the reason why I is decreased is because power equals I squared R. So the more current we have, the more power can get lost. Because when you increase the current, what happens? Resistance increases. So when you increase current, the resistance increases, which means there's more resistance. Don't forget, resistance is the blockage to the current. It's the blockage to the flow of electrons. And if we're blocking the flow of electrons, what's the issue with that? The issue with that is that more heat energy is lost. So that would mean in these wires, more heat energy will be lost. Um, so that would be make our electricity even more expensive. At the step down transformer, it reduces it to about 30,000. Then it's transferred to our local, as in it reduces 30,000 to go to a local generator. And then when it goes to our homes, it's reduced to 230 volts. That just makes it safer. 400,000 volts or 30,000 volts would melt our devices. So 230 is quite safe. So step-up transformers are used at the power station to increase the potential difference, the voltage, before electricity is sent through the transmission cables. When voltage goes up, the current goes down. So this is what I was just explaining. When voltage goes up, current goes down. Lower current means less heat is lost to the surroundings through the cables, and that is due to lower current means lower resistance. This makes the energy transfer through the national grid much more efficient. Okay, this is our transformer equation now. If you do the voltage of the secondary coil times the current, it is equal to the voltage of the primary coil times the primary coil current. That's because power is conserved. And power equals IV. So again, we've got lots of examples here for you to have a go at. Okay, now we're at 13.11p. Now, if anyone's doing combined, you are more than welcome to leave now because the rest of the session will be purely triple. So advantages of, so thank you for attending. So energy is dissipated. So advantage of power transmission. Why is power transmitted at in high voltage cables? So energy is dissipated in the transmission wires. That means energy is lost to the surroundings. And that causes power loss because power equals I squared R. Transmission cables have resistance. So because they've got resistance, we are looking at it from this formula perspective. So transformers are used to step up to a high voltage due to the relationship that power equals IV. Now, if current is low and less energy is lost, that means the power loss will be smaller as well. Okay, thank you everyone. That's the end of topic 13. So now okay, so let's continue. And we are continuing with physics, Edexcel paper 2, topic 11, static electricity. Okay, so static electricity. So charging insulators. When certain insulating materials are rubbed against each other, they become electrically charged. So negatively charged electrons are rubbed off one material and onto the other. So you can see that what's happening here, that negative electron is moving across. And what we now have between the two is a potential difference because we have positive here and negative here. When you have positive, when you have that potential difference between two things, that can cause a spark. That's how static electricity is created. Now, when certain insulating materials are rubbed against each other, they become electrically charged. Now, negatively charged electrons are rubbed off one material onto the other. So this is what we were just seeing on this slide here. The negative electrons are being rubbed off the cloth and going onto the plastic. So that's making the plastic more negative, and relative to the plastic, that means the cloth is more positive. So the material that gains electrons becomes negatively charged. The material that loses electrons is left with a equally positive charge. Now, what happens when two electrically charged objects are brought close together? So when two objects with electric charges are brought near to each other, they exert a force on one another. Two objects that carry different types of charge attract. So if this was positive and this was negative, they would attract to each other. If they're the same type of charge, they repel each other. And attraction and repulsion between two charged objects serve as examples of non-contact force. So static forces are non-contact. And we've got some examples here. So we've got a balloon attaching to a wall, a comb picking up paper, getting a static shock, lightning, all these examples of electrostatic phenomena or electrostatic shock or just electrostatic. So let's have a look. Objects with the same charge repel each other. So what happens here is this balloon has been rubbed against someone's shirt. So we've all done this. You get the balloon, you rub it against your shirt, and by rubbing it against your shirt, that balloon, all the negative bits, it loses negativity onto the person's shirt or onto the sleeve, whatever they're rubbing against. So now it's positive on this side. And this side is negative. So now let's say we take the negative side of the balloon towards the wall. What the negative side of the balloon will do is it will repel all the electrons. So temporarily, the wall becomes positive. And so you get attraction between the positive part of the wall and the negative part of the balloon. Now, what happens over time is the electrons move back to because the electrons aren't, well, the electrons will naturally start moving around again, and this region will become neutrally charged. What will eventually happen here as well in the balloon is that everything will start moving around, so it becomes neutrally charged again. So eventually they will separate. So the negative charges on the balloon attract the positive charges on the wall. More than that, they push the negative charges away. Now the comb now has a charge, so you just rubbed it against your shirt. It induces an opposite charge on the paper in the similar way to what the balloon did, and now the oppositely charged objects will attract each other. Now a person's been walking and there's been a transfer of electrons from their socks or shoes or carpet to them. So that means they become negatively charged. When they touch another object, there's a potential difference between them and the object. So even this escalator has been moving all day. It could be if you're walking up the stairs and you touch the metal at the side, and there's a difference in your charges if there's a difference in your charge and the thing you're touching, then there's a potential difference between the two. Electrons transfer from the person to the object and then to the earth, and then that earth's the charge. So what's happening is the electrons transfer from one person to the other. That's why sometimes you touch someone and you feel that kind of spark. It's because electrons have transferred from one person to the other, so that, and then the other person's felt it more because they're earthing it. It's now going through their body to the earth. Okay, earthing. So even in plugs, the earthing removes excess charge by the movement of electrons. So the earth wire is really important. If there are any excess electrons, it carries them away and takes them to the earth. As in, it takes them out of the device, is what earthing means. So how can dangerous levels of charge be removed? The earth wire removes the excess electrons. And ultimately, what does that mean? That means that the device won't melt. It's carrying that charge away. Okay, so the same thing happens in these different examples here. You've got insecticide sprayers. Now, if you're constantly spraying with the with the insecticide sprayer, you've got that spray moving past the plastic, so that can cause changes in charge. So the spray is actually this is a separate point here. The spray is electrostatically charged. So you know that the point where you spray from, that's electrostatically charged. And that means all the particles have similar charges and repel each other as they fall. So essentially what we're saying here is that you've got all the insecticide together. Before they're released, they through the nozzle, they're given a charge. So they get charged up as they're going out. And when they leave, because they all have the same charge, they repel each other away from each other. So you get a more spread out spray. Same thing happens in a photocopier. The small particles from the photocopier are charged before they're released. So that way they're more attracted to the paper. It also gives a more even spray. Spraying a car. The car will be negatively charged. If the paint particles are positively charged, they repel each other as they sprayed. And because they repel each other as they sprayed, it does exactly what this is. It spreads it out more. So you get a nice even spray, but also it's attracted to the car. So how does sparking occur? Sparking happens when there's a buildup of electrical charge, when a buildup of electrical is suddenly discharged through the air. This occurs due to the breakdown of air as an insulator. So, for example, I'll give a separate example first. Let's say someone has a kite flying right by um, power lines. Now, the power lines are live. Now, even though the kite isn't touching it, what can happen is the air that's around these charged wires can become ionized, meaning they gain energy and the electrons move to a higher energy level to the point that they become free from the atom. So then they become positively charged. Now, that positively charged part of the air can cause ionization of the next part of the air, the next part of the air, the next part of the air until it reaches the kite, at which point it can now travel through the kite and be grounded. So that's one example. But the example they're given here is more, I think linked to a lightning. So you can have a charge build-up. Static charges build on an object, for example, when you rub a balloon. Now, high electric field strength. The field becomes strong enough to affect nearby air. Now, it affects the nearby air, then the air becomes ionized. So electrons are removed from the air molecule, making the air conductive. And then there's a sudden discharge. Charge flows through the air, creating a visible spark. So that is what lightning is. But that can happen with the example I gave as well, with the kite going too close to power lines. So what are the dangers of sparking? So here's another danger. Sparking is particularly dangerous when they are flammable fuels, gases, or high concentration of oxygen. So a spark could ignite the fuel gases and cause an explosion. That's why mobile phones should not be used at petrol stations, because at the end of the day, that's microwave energy, and there's always going to be that concern um, that that energy can cause a spark. So it's also dangerous when you touch something with a large electrical charge on it. The charge will flow through a person's body, causing electric shock. And this could cause burns or stop the heart. It could cause burns or cause the heart to stop. Okay, so electric field. I would advise trying as many past paper practice questions as you can on this topic, because unfortunately it is one of those topics that's poorly understood. So what is an electric field? So the electric field is the region around a charged object where it exerts a force on other charges. It describes how electric forces act at a distance. So, in other words, an electric field is an invisible area around a charged object where it can affect other charges, even without touching them. So, think of it like a region where pushing and pulling can occur. Now, so here, that region there outside, so the surface of this hollow sphere will get charged up. That's the electric field around that hollow sphere. So that has been charged up. So it's an invisible region around that charged object where it can affect other charges. That means it can do what a magnet does. It can attract, repel, etc. Now, let's go through these key points. So the first thing is field strength. So the field strength, it says here, the strength of an electric field depends on the charge producing it and the distance from the charge as well. So a stronger charge creates a stronger field. So first thing, if you've got stronger charges, if you've got a stronger charge producing that field, then it's going to be a stronger electric field. Also, the further you get from that electric field, the less you're going to feel that electric field. So electric field strength just tells us how strong the electric field is. Now, it depends on the size of the charge. So the bigger the charge, the stronger the field. Also, it depends on the distance from the charge. So if you're closer to the charge, you're going to feel a stronger field. If something's further from the field, they're going to feel it to be weaker. It's going to get weaker the further you move from it. The same as a magnet. Like a magnetic field, it gets weaker as you move away. It's stronger the closer you get to it. The stronger the magnet is, the stronger the magnetic field is. Same thing here. The stronger the charge, the stronger the electric field. In that respect, it's very, very similar. Now, the field direction indicates how positive charges move. So, with lines pointing away from positives and towards negatives, when you have a positive, the electric field goes outwards. If these charges were negative, the electric field will come inwards. So, the field lines show if it's a positive charge or negative. So, if it's a positive, it goes outwards, it points away. If it's negative, it points inwards. So, in a sense, that helps us visualize the push or pull that it's having. So if something interacts with an electric field, something that has a charge, if it's a positively charged electric field, if, for example, put something here that was positively charged, it would push it away. Negative charge pulls things inwards. Now, field patterns. A single charge creates a radial field, while two opposing charge create a uniform field between them. So what that means is, if you've got where you've got the surface charged up like this, what that means is the electric field goes outwards like that. But if you had two charged particles like this, in between them, so let's say that's positive and that's negative, in between it you would have a uniform field going from positive to negative. So you can see the shape. In fact, you know what, just before we move on, let's just discuss a few of these things. So what we've got here is a pulley and a metal brush. Now they rotate the belt. If you can see the belt there, the blue belt that's going around this and going around the pulleys, it causes that charged conveyor belt to keep moving, rotating around in circles. And then you've got a metal brush, and what the metal brush does, it adds or collects charge to form the moving belt. So this metal brush, that's really important because that's either taking electrons off or is giving it its electrons. So in this case, from this one, it's taking the electrons. That's why it's a positive charge. Then you've got the charged conveyor belt that moves the charge up to the top using the motor and the pulley. So it's charging up here, but then it's taking it up to where the hollow metal sphere is. And finally, the collecting brush, which is this one, it collects the charge and then it puts it onto the hollow sphere. Now what the hollow sphere does, it collects and it stores the electric charge. So the electric charge is being stored on the outside of it, on the surface only. If it's positive, it exerts it outwards, and if it's negative, it takes the electric that shows the charge going inwards. So to quickly summarize just this slide, the electric field is an invisible force, or a visible force area around a charged object. So it's this area around that charged object. It gets stronger as you get closer to it, and if the charge is bigger, it's also stronger. And the direction, if it's pointing outwards, it shows it's positive. If it's pointing inwards, it shows it's negative. Okay, now we're looking at the electric field pattern around an isolated sphere. So the electric field pattern for an isolated charge sphere depends on whether the charge is positive or negative. So you just need to remember these key features if you get a question where it asks you to draw, whenever you draw the radial field lines for electric charge, if it's positive, it always goes outwards like this. And if it's negative, it would be like this. But of course, all the way around. Next thing is you have even distribution. So the lines are evenly spaced and point straight out. So you can see that here, they're evenly spaced and they're straight lines. Strength variation, it's stronger near the surface, weaker as you get further away. And there's no field within the sphere. So what some people do mistakenly is they start the line from the middle. But if you think about what I just explained on the previous slide, that collecting brush, where does it send the positive charge or negative charge? Only on the surface. So there's no charge on the inside because it's a hollow sphere. So 14.1 kinetic theory. There's no other matter. So what is matter? All matter is made up of tiny particles. There's no other matter except these particles. So particles of any given substance are all the same. They are, so if we're talking about gold, then what we mean by that is all the atoms within gold are the same. Then there's attractive forces between particles which differ from one substance to another. So we've already learned about that in chemistry as covalent bonding, ionic bonding, and metallic bonding. So how do we model the arrangement of particles in solids, liquids, and gases? So the arrangement of particles can be modeled by drawing particles as a solid sphere. So we can show all the particles are close in a regular arrangement with no gaps. That's our solid. In our liquid, you can see here, the particles are still quite close, but they have a random arrangement and there's still no gaps, or there shouldn't be gaps. And in a gas, the particles are far apart, have a random arrangement, and there's gaps. So you need to know how to draw solid, liquid, and gas. It is more of a foundation question, but you should have an understanding of how they're drawn. You should know the limitations of modeling particle arrangements in this way. So particles are shown as solids. So when we just draw circles like this, there's a presumption or an assumption that they are solids, which is not the case. Uh, and the particles are shown as spheres, which is not the case as well. As we know, atoms are predominantly empty space. We have a central part in the middle, which is the nucleus, and we have electrons orbiting in shells. It doesn't show the forces between the particles, so it doesn't show the interaction between the different atoms, and it doesn't show the speed of the particles. So of course in solid we have some kinetic energy, we've got this some vibration, some movement. Liquids have got more kinetic energy because to make a liquid you need to have increased the temperature. You have to have caused it to melt. So if someone increases the temperature, automatically they've provided each particle with more energy. And then in gas, that's going to have the most amount of speed, the most amount of energy, because you have to heat it up to quite a high temperature to turn it into a gas. And it doesn't show the speed, it doesn't show the movement, and it's only two-dimensional. So these are all limitations. Okay, now what we're about to go over the next few slides, as in what are the typical properties of solid, liquid, and gases. This is one of those topics that students try to wing in the middle of the exam. If it comes up, it's easy marks. So don't lose the marks because you made the assumption that, oh, I know this already, because you've probably learned this since you were in year 7. Some of you in primary school as well. So make sure you learn the key terms. So in a solid state, the particles are close together. They're unable to move away from their neighbors. When within a solid, the particles are vibrating. Solids are dense as the particles are close together. So we have a regular arrangement as well. Now, it's high density. What do you mean by high density? It means the particles are close together with little space between them. So within a given volume, when we say something is dense, for example, if we had 4 particles, um, 5 particles, and if we had the same space, but within that space we have more particles, then we say that that is more dense. So this is high density. This top one has a lower density because there's less particles within the same space. So solids are the most dense. They're hard to compress because the particles are close together with no room for particles to move closer. And the shape is fixed. Because what you've got between each particle, each atom, is a strong force of attraction. And the particles are held strongly together with those strong forces of attraction. Now in a liquid, the particles are also close together, but they can slide past each other. So within a liquid, that means they're able to flow. So you have the particles are vibrating, they're jostling around, moving around. The liquids tend to be dense as the particles are close together. So they have a higher density than gases because the particles are close together with little space between them. They're hard to compress because the particles are close together with no room for the particles to move closer together. And they can flow and fill the bottom of a container. And that's because the force of attraction between particles are weaker than in a solid, and so they're able to move freely past each other. To go from a solid to a liquid, some of those bonds, some of those forces of attraction have to be broken, which then allows it to move, gives it more flexibility to move around, but the particles are still joined to each other, so they can't move for example, from the bottom of a container. Now, in a gas, the particles are further apart. They've got the most amount of energy because all the bonds have to have been broken. They can move freely because all the intermolecular bonds that was holding to and the covalent in ionic or metallic bonds between them have been broken, which means they're now free to move as they wish. Not as they wish, but they're free to move. In a gas state, the particles are moving freely in random directions at different speeds. Gases are not dense because there's lots of space between the particles. So they have a low density. They can be compressed because there's space between the particles, which means they can be compressed and brought closer together. They can flow and they can fill a container. Now there's very small force of attraction between the particles, so they move out randomly and they can spread out in all directions. Okay, density. Now I'm aware you will be given this already, uh, that density equals mass divided by volume, but don't forget the units. So here's a really good example. Now, one thing with density that should be pointed out is that you can have kilograms, you can also have grams, you can have meters cubed, you can also have centimeters cubed. So if you did mass divided by volume and you had kilogram and meters cubed, then your answer would be kilograms per meters cubed. If you had grams and centimeters, then your density would be, the units for density would be grams per centimeter cubed. If you did the mass in grams and the volume in meters cubed, then density units will be grams per meters cubed. So you can have other, in density, there is that flexibility. So in this question, we've got a mass of 56. There's 56, and we've got a volume of 11.2 centimeters cubed. And it wants the answer in grams per centimeters cubed, which is good because we have grams here and we have centimeters cubed here. So it's 56 divided by 11.2, and the answer is 5. So the answer is 5 grams per centimeter cubed. Okay, so lots of examples here for you to go through. Now, actually, this one I will quickly go through. Now, we have a density of kilograms per meters cubed. So when we're calculating the volume, and we are going to do, um, we're going to do the volume equals the mass divided by the density. Now, in this question, because the density is kilograms per meters cubed, we have to convert that 1500 grams into kilograms so that you have that consistency. So how do you convert grams to kilograms? We divide by 1000. So that's 1.5 kilograms. Hence, we're doing 1.5 divided by 1200. So our answer is 0.00125, or to two significant figures is 0.0013 meters cubed. Okay, now core practical, this is quite a well understood, well known core practical, and it comes up quite often in papers. I've seen it in foundation exams and I've seen it in the higher paper too. So it's important to understand the paper, the core practical. And as I've advised with all the core practicals, my advice is to go to the Edexcel Pearson YouTube channel, and type in the name of the core practical and watch it live. Not live, but watch a person, an actual teacher going through it. So you can see all the parts and how they move and everything that you've got to do. So this, I will explain everything, but it's still advisable. So what is the equation that we would use to calculate density? We do density equals mass divided by volume, which we already know. So that means if we want to work out the density of something, we just need to find out its mass and we need to find out its volume. How do you find out its mass? Using a mass pan balance. And its volume, you can just measure it. If it's a regular shape, you can just measure all the sides and calculate the volume. Now, if it's an irregular shape, then the process is a little bit different. Now, mass is the amount of matter, so it's the amount of particles or atoms within something, and it's measured in kilograms. It's a scalar quantity, meaning it has no direction, but it does have magnitude or size. Volume is the amount of space an object takes up. It's measured in cubic meters. And density is the measure of how much mass is packed into a certain volume. So if you've got a regularly shaped cube, cuboid or regularly shaped any shape, all we have to do here is use our mass pan balance and find out the mass. We get the ruler and we measure the length times the width times the height, but we use a ruler. And we now know what the volume is. And then we simply put the mass into the density formula. We substitute in whatever our mass was from the mass pound balance and whatever volume we just calculated, and we now know the density. So if it's a regular shape, it's simple. Work out the mass using a mass pound balance, work out the volume using a ruler and doing a calculation of length times width times height, and just do mass divided by volume. Now if you have an irregular shape, you can put water in a eureka can. Now the mass is measured in exactly the same way. You would use a mass pound balance. But the volume, because it's an irregular shape, such as this chess piece, you use a eureka can, you pour water until the water level is just below the spout, which is just here. Then you have an empty beaker underneath it. You put your shape inside. So you put your piece inside. Now, when you put your piece inside, that displaces water. So the water level rises. All the excess water now pours out. The water that pours out represents the volume of that shape, that object. So now you have a mass and you have the volume, because the volume is the displaced water, which means you can work out the density. So that's what it's saying here. Place the item in the beaker, ensuring it's fully submerged beneath the water, and determine the amount of water that's been displaced. Position the empty beaker under the spout. And then that means we have the mass and we have the volume. Now, what are possible sources of error when finding density? So we could have a random error. That happens when a person makes mistakes while taking measurements. For example, reading the ruler from the wrong angle. It could be when you're reading the beaker, you're finding out what the volume of the water is. There could be a parallax error, meaning you could read it from the wrong angle. Now, when you're reading, if you have, for example, a measuring cylinder, and you have your reading here, your eye level has to be on line with where the water level that you're measuring. If you look at from above, you're going to see a number which is lower or potentially higher. So depending on which angle you're looking from. When you look from below, you're going to see the wrong angle too. So it's important to look at it from look at it from eye level. Then zero error. That happens when you use, for example, mass pan balance and you don't zero it properly. So if your apparatus does have a zero error, the way to correct it is really simple. Now usually we just press tear and it goes back to zero. Now let's assume what you have got, even after tearing it, it doesn't go back to zero. And then all you do is you take away 0.12 from your final mass. And here we've got parallax error. So if you're looking from below, you're going to see that smaller number. If you're looking at it from above, you're going to see that bigger number. So it's important to only look from eye level. Okay, density of materials. So in a solid, the particles are closer together. So it's more dense. A liquid, so it's like what we've just covered. Density is the amount of particles within a given volume. So if we said this was the given volume, if we compare the number of particles in each one, then we can see that you have the most number of particles here. The liquid is still dense, but not as dense as solid, and gas is not dense at all. Okay, you need to know the state changes. Again, this usually comes in foundation, but there are calculations that link to the state changes that you need to be aware of. You still need to understand the science from just a basic state change perspective, as in, if it goes from solid to liquid, what's the state change? That's foundation. But the explanation of why something goes from solid to liquid, why you have no change in temperature for a certain amount of time, etc. That is both papers, but more higher. Now, melting point is the temperature when a solid turns into a liquid. Condensation point is the other way around, when a liquid turns back. No, sorry. Freezing point is the opposite of melting, which is the temperature at which liquid goes back to being a solid. Then you've got boiling point, the temperature when a liquid turns into a gas. And then you've got condensation point is when that gas turns back into a liquid. Now, what has to happen for it to go from one state to the other? To change state, the forces between the particles must be broken. So in a solid, you've got this regular arrangement. For it to go to a liquid, where your arrangement is, they're still touching, but they're a bit more irregular, some of the bonds between have to be broken. So stronger forces between particles means a higher melting point. So usually anything that has a covalent bond, well, the more covalent bonds are stronger, higher the melting point. The more ionic bonds, the higher the melting point. Well, ionic bonding has high melting points anyway, or boiling points. And same with metallic bonding. So what happens when a substance is heated? When a substance is heated, the energy stored within the system will increase. So what we're saying here is, if you've got an ice cube, to break those bonds to turn it into a liquid, which way is the heat energy going to go? It's going to go inside. So what's happening to so on the outside, it will feel like it's really cold. If you have a thermometer here, it will seem as though it will show the temperature will stop increasing because all the energy is going inside. That means the internal energy, the energy within the system, is increasing. So when we get to a liquid, the outside temperature might be slightly warmer, but uh, so ignore the outside temperature. We're talking more about the internal temperature. Internal temperature will be higher now because more energy has been taken in. So this increase in energy stored can be used to raise the substance's temperature or produce changes in state. So that energy that's going inside, that's being stored, and that increase in internal energy is being used to break the bonds to change it from one state to another state. Okay, specific heat capacity. So this is linked to what we've just said in 14.6, is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree. So if something has, so let's look at this copper block. Let's assume that copper block weighs 1 kilogram. Okay, now this jouleometer is attached to this immersion heater. It provides energy to the immersion heater, and that starts to increase the temperature. That's why we have a thermometer to measure the temperature. So specific heat capacity is the energy in joules required to increase the temperature of 1 kilogram of a substance by 1 degree. So for example, this copper block is the amount of energy that's being supplied by the jouleometer to change that temperature there from 1 degree to 2 degrees. So specific heat capacity, or change in energy, equals the mass of whatever you're measuring times specific heat capacity times the change in temperature. So specific heat capacity is the change in energy divided by the mass times the change in temperature. Now, latent heat. So when we talk about specific heat capacity, We're talking about the energy needed to make the temperature increase. So if something is, for example, at minus 15 degrees, it might be working out how much energy is required to take that temperature all the way up to 0 degrees. Now, latent heat is the energy required to change the state of a substance, like melting or boiling, without changing its temperature. So specific latent heat is the energy needed to change the state of 1 kilogram of substance without any temperature change. So if we look at, there's a slide that's coming, and never mind, but I'll explain it here. So what we're saying is, when we say, let's use the example of an ice cube, because it's important you know the difference between specific heat capacity and latent heat, specific latent heat. So we've got an ice cube and we're at minus 10 degrees. Now, what temperature is it going to melt at? It's an ice cube, so it's going to melt at 0 degrees. So that initial, so now to increase the temperature, what do we need to do? We need to increase the energy. So I've got my beaker and I'm providing heat energy to it, and my ice cube is absorbing that heat energy. It starts breaking it down. Now, as long as it's below 0 degrees, is it going to melt? No, it only melts at 0 degrees. But the temperature needs to get to 0 degrees before it melts. So what we're saying here is, this is the time taken. We turn the Bunsen burner on, the temperature starts to increase. Now, you see this initial phase here, you work out the energy required to get it to 0 degrees by doing the specific heat capacity formula. So change in energy equals mass times specific heat capacity times the change in temperature. Then when it gets to 0 degrees, it starts to melt. But for a certain amount of time, for a few minutes, that it doesn't change temperature. Why is it not changing temperature? Because all the energy is going inside. All the energy is going inside to break the bonds. No energy is going to the thermometer to make the temperature increase. So look, this is specific latent heat. Here, to find out the amount of energy needed what we're working out here is the amount of energy needed to make it change from a solid to a liquid, or a liquid to a gas. So if we look at step one, we're trying to find out the energy needed to just increase its temperature. That's what specific heat capacity is. That's the energy chain linked to specific heat capacity. Phase two is the amount of energy needed to actually melt it or boil it. So if you look at the definition of specific latent heat, what does it say? It says the energy needed to change the state of 1 kilogram of a substance, 1 kilogram of a substance without any temperature change. So how to change the state of 1 kilogram of substance without any temperature change. So here we have no temperature change. We're just changing the state of it. And for this, the formula is just here. 14.9. The change in energy equals mass times the latent heat. So you need to know the difference between the two. Stage one, we're just causing the change, we're causing it to increase in temperature. So if you have a question that says it's at minus 10 degrees, how much energy is needed to melt it? First thing you've got to do, if it's at minus 10 degrees, is increase its temperature to 0. So how do you work out the energy change? Change in energy equals mass times specific heat capacity times change in temperature. In other words, this formula. Then it says we're at 0 degrees, it's going to melt. How do you find out the energy change there. Energy change equals mass times latent heat. So you need to know both these formulas. You need to know the difference between the formulas. So when we say specific latent heat of fusion, it's the amount of energy needed for the substance when a substance changes from a solid to a liquid. So without changing the temperature, it's just the amount of energy needed to change 1 kilogram of substance from a solid to a liquid. And the specific latent heat of vaporization is the energy needed to change 1 kilogram of a substance from liquid to gas. Liquid to gas with no temperature change. Now, we've already discussed this formula, but you do need to know the units. There's no interchangeable units here. Mass is kilograms. In density, you can have kilograms or grams, but here in specific heat capacity, it's not interchangeable. So there's lots of practice questions here for everyone to go through in their own time. Of course, the best practice questions are in past papers. Now, when we calculate latent heat, energy for a change in state. So don't forget, the energy change that's linked to specific heat capacity is just how much energy is needed to make the temperature increase. Here, when it's change energy equals mass times latent heat, specific latent heat, we're talking about the amount of energy needed to make it just change from a solid to a liquid, from a liquid to a gas. At that point, there's no change in temperature. Because where's all the energy going? It's going inside the substance, inside the solid to break the bonds to turn it into a liquid. Or it's going inside the liquid to break all of the bonds to turn it into a gas. So again, there's lots of practice questions here for you to go through. And again, the best practice questions are the ones in past paper practice. Okay, so how can we reduce unwanted energy transfers? So one way is thermal insulation. Examples in the home include the loft insulation, carpets, anything that reduces heat loss. There's cavity wall insulation. So in a lot of the modern houses, you have a gap between, so when they build the brick walls, they do two thin layers, and in between they put insulating material. All the insulation does is it reduces the transfer of energy. So this core practical is how can you use apparatus to determine the specific heat capacity of a material. So if you understand the apparatus, it makes the whole experiment so much easier. So you've got your metal block. It usually looks like this, and it has a hole inside it so that the immersion heater can enter. So you put the immersion heater inside there. So let's have a look. Let's take an immersion heater. It goes inside there. And if we were showing it inside, it would be inside. And that immersion heater is then attached to a joulometer, which is attached to a power pack. And then there's another hole that has the thermometer inside. So you can measure the temperature change as well. Now, and this is the material for which you're trying to find out the specific heat capacity. Now, how do you work out specific heat capacity? We do change in energy. Now, how do we find out the change in energy? Using the joulometer. That will give us the energy change. We're dividing that by the mass. Now, it's usually a kilogram copper block, but you can weigh that on a mass pan balance and know what the mass is. And we change it by the measure time multiplied by the change in temperature, because we know the starting temperature, and when the experiment finishes after a certain number of minutes, you can then check the final temperature, take them away. So you measure the mass of the material by using a mass pan balance. Okay, that's straightforward. The thing is here, if we know the formula, which will be provided to you, you just have to explain how you're going to get each part of the formula so you can work out specific heat capacity. Then you add the heater, the immersion heater, to the block, and connect this to a power pack and connect that to a joulemeter. Add a thermometer and record the start temperature. Then you turn the power pack on. After 10 minutes, turn the power pack off. Record the change in the joulemeter, how much energy has been transferred. Measure the change in temperature, and then use this equation. So specific heat capacity equals a change in energy, which we got from the joulemeter, divided by the mass, which we got with our mass band balance, times the change in temperature. And how do we get change in temperature? We use our thermometer. So we now have everything to work out specific heat capacity. So this just summarizes what we just said. How do you find the temperature change? Use a thermometer to record the start and end temperature of the block and just subtract the numbers from each other. How do you find the mass? Use a mass band balance. How do you find the energy supplied? You measure the energy supplied using a joulemeter. And then how do you work out specific heat capacity? You use this formula. So you rearrange the formula that's given here so that the C, which is a specific heat capacity, is the subject. Okay, now why might you not find the exact specific heat capacity of a material using this equipment? Because this will mean the specific heat capacity calculated. So look, to reduce the heat loss in the block, you can wrap it in an insulating layer. Some of the heat energy will be lost to the outside. So some energy will be transferred to the surroundings and won't heat the block. So that energy is lost. The temperature will not rise as high as it should for the energy transferred. So if you wrap this up with an insulating layer, more energy will go towards heating up the thermometer. So this means that the specific heat capacity that you've got will be lower than it should be. But if you wrap it in an insulator, then your answer will be more accurate. Okay, pressure of gases. So what is the movement of a gas, of particles in a gas like? So when we say, let's start with the word, what do we mean by pressure? So pressure equals force divided by area. So when something collides with something else, so for example, if you have a balloon and you put air into the balloon, then every time one of the air particles hits the side of the container, side of the balloon, it exerts a force across an area, and that's pressure. So gas particles move randomly and rapidly in all directions. They're widely spaced and have no fixed positions. So as the temperature increases, the particles gain kinetic energy and move faster. Now, if they're moving faster, if you increase the temperature of something, you increase the kinetic energy. That means they move faster because kinetic energy equals half times the mass times the velocity squared. So if you increase kinetic energy, you increase the velocity. When the gas particles collide with the walls of a container, they create pressure. So when the particle hits, that's pressure. So in other words, higher temperature means it moves faster, it hits the side of the container more often, so you get an increase in pressure. That's if the volume stays the same. So why does pressure of a gas increase when its temperature is increased? So what we've just explained already, when the temperature increases, you're increasing thermal energy. The gas particles absorb that thermal energy, and that thermal energy is converted into kinetic energy. So kinetic energy increases. If kinetic energy increases, the mass isn't going to change. The only thing that can change is the velocity. So they move faster and faster. Now, if they're moving faster and faster, it means they're going to collide with the walls of the balloon or the container that they're inside more often. Each collision is an exertion of force. And each collision happens with more force because it's moving faster and faster. So the more times we have collisions, more collisions means an increase in pressure. So absolute zero. Now, absolute zero is the temperature minus 273 degrees. This is the temperature in which there's a lack of any movement of particles. So what we're saying at absolute zero, because absolute zero is equivalent to 0 Kelvin. So what we're saying is 0 Kelvin or absolute zero, the temperature is so low that in theory the particles don't have enough energy to move. So this I've seen this come up maybe once in the last 7 years, twice in the last 7 years, but it will be in the hopefully in the mathematical section of the pre-exam workshop. So it's not something that comes up often, but it has come up. Each degree Celsius is the same as 1 Kelvin. So if you raise the temperature by 1 degree, you also increase by 1 Kelvin. So to convert from degrees Celsius to Kelvin, you just add 273. To convert from Kelvin to degrees Celsius, you just subtract 273. Okay, 14.6p. We are towards the end of this presentation now. The remainder of this presentation is triple award only. So compressing and expanding. So how can a gas be compressed or expanded? So a gas can be compressed or expanded by pressure changes. So the pressure produces a net force at right angles to the wall of the gas container. So what this essentially means is if we increase the pressure, as in we push it from this side, we push it from this side, or we reduce the space that's provided, so all the particles are now within that smaller space, we've increased the pressure because now all the particles, the more particles hit the side of the container. The more often these particles hit the side of the container, the higher the pressure. But sorry, so what this is saying is a gas can be compressed or expanded by pressure changes. So another way of looking at that is if you have, for example, a balloon and it has lots of air particles inside. Now, if you put that into an area, if you put that into um, if you put it into a locked room where you can change the pressure, if you increase the pressure on the outside of the balloon, so you've got lots and lots of particles around the outside of the balloon, more particles on the outside than the inside, then what that means is you have more particles hitting the outside of the balloon. Now, on the inside, the particles will still hit the inside of the balloon and exert a force, in other words, have a pressure. But we're saying there's so many particles on the outside that the particles on the outside are a bigger force. There's more pressure on the outside than there is on the inside. So what will happen is the balloon will become smaller. They become smaller because there's more particles colliding on the outside. Now, if you put it again in a sealed room where you can change the pressure, I'll just do it as dots this time. So these are all particles. And this time you 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 have all the air within the room, but you're able to remove all of that air or reduce the amount of that air. So by reducing the air now around the balloon, you've now got a greater pressure on the inside. So more particles are hitting the side on the inside. you've got less pressure on the outside. So now that balloon will increase in size. So what causes gas pressure? Pressure in gases is caused by particles colliding with the walls of the container. When the particles collide with the walls of the container, a force is exerted. So essentially what I've been explaining from the start. So the greater the force, the greater the pressure, because pressure equals force divided by area. So the bigger the force, the bigger the pressure. The more collisions, the greater the force. So why does pressure increase when the gas is compressed? So again, if we compare the two, here we've got less space. And what that means is the particles are closer together. We've got a volume that's been decreased. The particles are now closer together. So that means they're going to collide with the walls more often. Now, every time one of those particles hits the wall, it exerts a force. And the greater the force, the greater the pressure. So the more frequent collisions means more force on the walls, which is an increase in the pressure. And again, you'll be given this formula in the exam. So it's just a matter of understanding what the different units are. And again, the best way to practice formulas is past paper practice. But in the pre-exam workshop, all of that, we'll be going through lots and lots of maths as part of our revision. Okay, so up next is topic 15. So topic 15 is from Physics, Edexcel Paper 2. Topic 15, forces and matter. So if you applied a force to compress both a spring and a drinks can, what difference would there be? Why do you think this is? So if you had, for example, a spring and you push down the spring, what's the spring going to do? You'll cause it to compress. When you stop exerting that force downwards, it'll spring right back up and it'll go back to its original shape. And that's because it's an elastic object. Now, if you think of a soda can or a drinks can, if you put your force down on this can, you're going to compress it. But because it's an inelastic object, it won't spring back up. So when a force is applied to either of these objects, they'll change shape, and depending on the force applied, they may bend, stretch, or compress. So when we have a change in shape, we call it deformation. So there's three key words here. Elastic object, that's one that goes back to its original shape. Inelastic object, that's something that doesn't go back to its original shape. And deformation. Things deform when they have changed shape. So this is elastic deformation because it's reversible. So if the deformation is with an elastic object, then up to a certain force, it always goes back to its original shape. But when you have an inelastic object, when you exert a force, when you remove that force, it won't go back to its original shape because it's inelastic. Okay, so what is the equation that you would use to calculate the extension of a spring? So if you've got something, we just said here, has an elastic deformation, then you can calculate the energy that you're putting into that object, into that elastic object. And you can do that by doing force equals spring constant multiplied by the extension. Now the spring constant is um, exactly that. It's a constant that connects force to extension. So when you do direct proportion in maths, you might, for example, have y equals kx. And k is the value that connects y to x. That's exactly what's happening here. K connects force to extension. You will still be given this formula, so make sure you remember the units. Now, when you work out K, you do force divided by extension. In other words, you do newtons divided by meters. So the units for spring constant are newtons per meter. So this is an example here that you can go through. Lots of examples, but again, where are the best examples? In past paper practice. So how can you find the work done when a spring is stretched or compressed? So a force that stretches or compresses a spring does work, because work done equals force times distance. So if you've taken a spring that was this big, you've exerted a force onto it, now we have force, and you've pushed it down, so now it's this big. You've taken it from here to here, so now you have distance as well. In other words, work has been done. So elastic potential energy is stored in the spring. So that work done is converted into elastic potential energy. Provided the spring is not inelastically deformed, the work done on the spring is equal to the elastic potential energy that's stored inside the spring. So when you have a spring that's this big, when you push it down, in those compressed cores of wire, you've got elastic potential energy. That elastic potential energy is equal to the work done. So in another way of, so we've already had here, force equals spring constant times extension. And to work out elastic potential energy, we do half times the spring constant times the extension squared. Now, when we say kinetic energy equals half times mass times velocity squared, and now we're seeing extension squared, do not forget the squared. It's so commonly forgotten. Even though this formula will be in your formula sheet, people still forget the squared. So the elastic potential energy, that's the energy that's stored when an object is stretched or compressed. So if you get a spring and stretch it out, or you crush it, you compress it and make it you kind of squeeze it between your fingers, or you push down on it to compress it, that's elastic potential energy. The fact that it springs back to its original shape, that's the energy being released. So again, lots of practice questions here. Really quickly, how do you convert centimeters into meters? We divide by 100. So again, lots of practice here for you to go through. Okay, below is a graph that shows the extension of a spring when a force is applied. So what relationship does this graph show? So what we've got here, firstly, is it shows direct proportionality from here to about here. And how do we know that's direct proportionality? Two reasons. Number one, it's a straight line. Number two is the straight line is going through the origin. So extension and force are directly proportional. So when we increase the force, so let's say you have a spring and we add a weight at the end of it. So in other words, we add a force. What's that force going to do to the spring? It's going to cause it to extend. So now we increase our force. What's that going to do? It's going to increase our extension. So we add another weight and we increase the force, and that causes an increase in extension. Now, the relationship between the force that's added and the extension of that spring is directly proportional. So as the force increases, the extension increases until we reach the limit of proportionality. At that point, the line begins to curve. Why? Because this means the relationship is no longer directly proportional. The relationship is no longer linear. This is the point where the spring stops behaving elastically. It stops going back to its original shape. So most people have probably done this at some point in their life, where they've got a spring, they've stretched it, it's gone back to its original shape. So they stretched it a bit more, it goes back to its original shape until they stretch it to a point where it no longer goes back to its original shape. The point where it didn't go back to its original shape, that's what we call the limit of proportionality. So at that point, it's no longer directly proportional. It's no longer a linear relationship between force and extension. At this point, you add a bit of force and it extends more than it should do. Now, the point where you have direct proportionality between extension and force, which on this graph is a straight line that goes up to about here, that's Hooke's law. So as long as it's a straight line and extension and force are directly proportional to each other, that means it's obeying Hooke's law. So the extension of a spring is directly proportional to the force applied as long as the limit of proportionality is not exceeded. So up until this point, it's obeying Hooke's law. Beyond that point, it is no longer obeying Hooke's law. So about there, it starts to curve. It's not following Hooke's law anymore. But from here, this whole section here, it's following Hooke's law. So again, this is really good core practical. I've already explained quite a bit of it. But again, my advice would be Edexcel Pearson YouTube channel. So set up equipment as shown in the diagram. Adjust the ruler so the 0 mark is at the same height as the top of the spring. So you can see the ruler should be just when it says the top, it should just be the bottom of the spring just there. Record the length of the spring when no weights are attached. Then hook a 1 Newton weight at the bottom to record the new length of the spring. Then you add another weight and record the length of the spring. Then you add another weight, record the length of the spring, add another weight, record the length of the spring, and so on and so on. So you add weights at 1 Newton intervals, recording the new length of the spring. That way, and each time you add that 1 Newton, you determine the extension of the spring when each weight is added by subtracting the original length from the recorded length. Because recorded length will be getting bigger and bigger and bigger. Now, why is this weight there? Is to stop all the apparatus from falling over. Now, 15.7, up until the end of this PowerPoint, is now triple award. So 15.7p, atmospheric pressure. So what is a fluid? Fluid just means a liquid or a gas. And in a fluid, the particles can move over each other, and so the fluid can flow. Now with atmospheric pressure, the atmosphere is a thin layer, well, thin relative to the size of the Earth, that is, of air around the Earth. Now, as you go higher, further and further away from the surface of the Earth, the atmosphere becomes less dense. That's because the particles become more spread out. You have less and less particles as you go further and further from the Earth's surface. So air molecules colliding with the surface create atmospheric pressure. So the further you go from the Earth's surface, the atmospheric pressure gets less and less. Why is that? Because you start to get less and less particles. So the higher up, if you're climbing a mountain, for example, because you've got less particles, less air higher up, there's less oxygen as well. So usually when people climb mountains, they have to practice in oxygen tents where the oxygen levels are slightly lower, and it helps the body adjust. The body starts to naturally make more red blood cells. It helps them adjust. So the number of air particles, air molecules, and so the weight of the air above the surface decreases as the height of the surface above the ground level increases. Meaning the higher up the mountain you go, the less you feel, the less of a weight you feel on your head. That weight that we feel on ground level is all of the air pushing down on us. The higher you go, because there's less air, the less pressure, the less weight you feel. So as the height increases, there's always less air above a surface than there is at a lower level. So you're going to have less air up here compared to down here. You're going to have a lot more air lower down. So atmospheric pressure decreases with an increase in height. So the pressure in a fluid is due to the fluid and atmospheric pressure. So this is essentially what we covered before, but it's understood with this formula here. The pressure in fluids causes a force normal at right angles to any surface. So if you have a surface, if the particle collides with it, if that's your medium line between the two different materials, it's always at 90 degrees to that surface. So if it collides over here, it's going to collide at 90 degrees to that surface. Now, how do you calculate pressure? And I've gone through this. I've mentioned this a few times since we started. Pressure in pascals equals force divided by area. And force is in newtons, area is in meters squared. So we've got some practice questions here. But again, the best practice is past paper practice. And what causes pressure in a fluid? So this is another formula. Pressure in a fluid. Now, one thing to understand here is if you have, for example, water and you're down at the bottom here. If you're at the top, you don't have as many particles colliding with you. If you're at the bottom, you have all of these particles colliding with you. So the pressure you feel at the bottom is going to be more than at the top. So pressure equals the height of the column, the density of the liquid, and gravity, gravitational field strength. Again, you'll be given this where pressure equals height times the density times gravity. This will be a formula in your booklet, but please make sure you know that pressure is in pascals, the height is specifically in meters, density is in kilograms per meters cubed, and gravity is newtons per kilogram. And again, we've got lots of practice here for you to have a go at. But of course, the best practice is the practice that is in past papers. Now, what causes upthrust? Now, a partially or totally submerged object experiences a greater pressure on the bottom surface than on the top surface. This creates a resultant force upwards. Now, let's just understand that. The next slide does explain it, so I want to go through this twice. So we have an object, and as that object sinks, what's it doing to the water? It's pushing the water to a side. And eventually, what happens when that water pushes to a side is it comes back and it ends up pushing it from below. Because what you're getting is pushing it to one side. So now you end up with an upthrust, an upward force. Now, at the point where the upthrust becomes a bigger force than the object, then the object will go right back up to the top again. Now, if the downward force is bigger, then even though there's upthrust, it won't go back up. So if you've got a piece of gold and you put it into water, it will just sink to the bottom. Because even though it's displacing the water and it has an upward thrust, and the particles that it's colliding in are pushing it back upwards, ultimately what that means is that force is always going to be bigger than the upthrust. But you have something like this rubber duck. If you push it down to the bottom, because the upward force is bigger, it will push that rubber duck right back to the top again. So what causes that upthrust? Now, a partially or totally submerged object experiences a greater force on the bottom surface than on the top surface. And this creates a resultant force upwards. So that means there's a bigger force upwards. Now, upthrust is equal to the weight of the fluid displaced. So the upthrust is the same as the amount of fluid that's been displaced. So the more fluid that's displaced, the more of the upward thrust. But you have to still keep in mind that if you're using an object that has a really big force downwards, then that resultant upward thrust won't have an impact. It won't stop it from sinking, which is essentially what it's saying here. So we've got a pumice stone. Pumice stone has lots of air gaps, and the obsidian stone has no air gaps. It's very dense. So if the upthrust is larger than the weight of the object will rise. So this has a downward force because it has a mass and a weight. It's going to go downwards. But the upthrust is greater, so it floats back to the top. With the obsidian stone, the downward force, the weight is bigger. The upthrust is less. The upthrust is not so much. So the object will continue sinking. And that takes us to the end of Physics Paper 2. So thank you everyone for joining us through the Biology, Chemistry and Physics AMALathon 2. That is the end of our sessions.